Okay, so today
I'll start with continuous functions, and we will try to understand the definitions of continuous function and how it is important. We will see various circumstances because from this definition we can predict some of the behaviors which we couldn't able to do before. For example, if you see this
see this
definition,
definition.
um, over
Um,
here we
Over
have
here we have
this definition
this
which tells
definition
you,
which tells you,
let's say you have a
let's say you have
function,
a function,
okay,
okay,
and it has a
and
limit
it
L,
has a limit L,
and in this
and
case
in this
the
case
function is
the
defined
function is defined.
the function is
The function
defined
is defined
at that
at
particular
that particular
x equal to
x
a.
equal to a.
So we know what
So
is
we
the
know
value
what
at
is the
that
value
function,
at that function
value
at that value
x equal to
x
a,
equal to a,
and that turns
and
out
that
to be
turns out to
f of
be
a.
f of a.
Okay,
Okay,
and this is
and this
shown
is
over here.
shown over here.
This is your
This is your
functional
functional
original
original
definition.
definition. Okay,
Okay,
that is
shown in
shown
the
in the
red
red
line.
line.
Now what we will
Now
do,
what we will
we'll
do,
first
we'll first
try to
try to
understand
understand whether this
whether
function
this
is
function is
continuous or not.
continuous. For example,
For
at x
example,
equal
at
to
x
a.
equal to a.
For that, we
For
will
that,
first
we will first
calculate what
calculate
is called as
what
a
is called as a
limiting value.
limit.
And if this limiting value is equal to this function value which is in the definition, then we can say that this function is continuous. Because for example, you can see in this particular diagram, we have value of the function which is not same as the value of the limits what we have got, because this blue color shows you the value of the limit. Okay,
Okay,
and this
and
red
this
dot
red dot
tells you the
tells
value
you the value
of the function which
of
is
the function
defined
which
at.
is defined at.
And here we can
And
see
here we
that
can see that
they are not
they
same
are
in
not
this
same
particular
in this
graph
particular
itself.
graph itself.
So we can
So we
conclude
can
that this function
conclude
is not
this function is
continuous
not
just by
continuous just by
graphically.
graphically.
Okay,
Okay.
now the way we can
Now the
write
way
down
we
this
can write down this
definition in
definition
epsilon
in
delta,
epsilon delta
by defining
by
an interval.
defining an interval.
For example, you will
For
give me
example,
an
you will give
interval.
me an interval.
I can always
I can
come up
always
with
come
an
up with an
interval on the
interval
x
on the
axis.
x-axis.
You give me an
You give
interval
me an interval
around this
around
value.
this value.
I can always
I
come
can
up
always
with
come
an
up with
interval
an interval
on the x
on the
axis
x-axis
such that
such that
the
the
values
values
in this
in
interval
this interval
will be
will
same
be same
to these
to
values,
these values,
right?
right?
The values and
The
the
values
actual
and the
values
actual values will try to
match
match
in this
in
level
this
of
level
confidence.
of confidence. Okay.
For that, you need
For
to
that, you need to
input
input.
input
You need
your
to input your
variables as
variables
this.
as this.
If you give
If you
input
give
of
input
these
of
values,
these
for
values,
example,
for
because
example, because
I
since
can always
I
come
can
up with
always
an
come up with an
interval.
interval
So
here,
if I
so if I
take the values
take the
from here
values from
and
here
feed
and
this in the
feed this in
function,
the function,
I will always
I will
end up
always
in the
end up in
interval
the
which you
interval
gave me.
which you gave me.
Okay, so this is the
Okay, so this is
definition
the
of this
definition
continuous
of this
function.
continuous function.
Now we will
Now we will
see
see an
this
equation,
function
this function
as an
as an
example,
example,
and we will try
and
to
we will
figure
try to
out
figure out
whether this
whether this
function
function
do have
do
any
have
limiting
any
value
limiting value
at x equal
at
to
x
0.
equal to 0.
And this
And
seems
this
that
seems
from
that
here,
from
if
here,
we
if
do a
we
quick
do a quick
calculation
calculation
and if we
and
check,
if we check,
the answer is
the
no.
answer is no.
So there is
So
no
there is no
limiting value
limiting value
in this
in
particular
this
function.
particular function.
Okay,
Okay,
because we see
because
that the
we see
domain
that
of
the
the
domain of the
function
function
is real
is
value
real value
except 0.
except 0,
This is
right?
the domain
This
of
is
the
the
function.
domain of the function.
And we were trying
And
to
we were trying to
understand
understand
the
the
continuity of this
continuity of
function
this function
at x equal
at
to
x
0.
equal to 0.
So the first
So the
criteria
first
is that
criteria is that
the function
the
should be
function should
defined
be
at that
defined at
particular
that
point.
particular point.
But as in this
But as in
example,
this
you can
example,
see
you can
the
see the
function
function
is
is
not
not
defined
defined
at
in
that
that
particular
particular
point.
point.
For
For
example,
example,
so we can easily straight away say that the function is not continuous at x equal to 0. Because the first basic thing is that you know what is the value of the function at that particular time. So that is the most basic fundamental thing which we need to know. Are you able to follow up what I'm trying to say? Can you give me one thumbs up? I'm going very
I'm
slowly,
going
okay?
very slowly. Like
Then I'll
then I'll
then I'll speed up.
then
If
I'll
you want
speed
me
up.
to
If you
speed up,
want me to speed up, I
you
can
can
speed
text
up.
me.
Just text me.
Am I audible to you,
Am I
right?
audible to you, right?
Just give me one thumbs
Just
up
give
so
me one
that
thumbs
I
up
can
so that I
get
can
the feel.
get the feel.
Whether do I speed
Whether
up
do I speed
or
up
should I go
or
slow?
should I go slow?
Okay.
Okay.
So this I
So
think
this,
this
I
idea
guess,
is
this
clear.
idea is clear.
So this idea is
So
clear
this
why
idea is
this
clear. Why
function
this
is
function
not
is
continuous at
not
x equal to
continuous at
0.
x equal to 0? Because I
Because
haven't checked the
first of all
limits.
limit
First
don't
of all, limit
exist.
don't exist.
That's the first
That's the
point.
first. That's the second
And the
point.
more
But the more primary point is that the function is not
that function
defined
is
in that
equal to
x
0.
equal to 0.
We can straight away
So we
say
can
that
straight
the
away
function
say
is
that the
not
function is
continuous at
not
x equal to
continuous
0.
at x equal to 0.
Now we will consider
Now we
this
will
function.
consider this function.
The only difference is that we have multiplied a variable x on it. Okay. So what happens? This variable x will create some important result. Will give a very good impact. Okay. Because of this, now we would be able to define a function at x equal to 0 in a limiting sense, not in the actual sense. Even if you see what is the domain of this function, it will still be written as this way. But if we see very carefully over here, if you see very
If you
carefully
see
over
very
here,
carefully over here,
this tells me
this
that
tells me that
the function
the
has a
function
limiting
has a
value,
limiting value,
that is
that
0.
is 0.
If I calculate the
If I
limiting
calculate
value
the
of this
limiting
function
value
at
of this
0,
function at
I
x
have a
equal to 0,
limiting
I have
value
a
as 0.
limiting value as 0.
So in order to
So in
make
order to make
this continuous,
this
first I need
continuous,
to
first I need to
redefine this
redefine
function.
this function, right?
This function
This function
is not defined
is
at x
not
equal to
defined at
0.
x equal to 0. So what I can do, I can
I can
redefine my
redefine it
function
such
such
that
that I will
I
assign
will
I
assign
will assign
0 to my
0
x
to
equal
my
to
x
0.
equal to 0.
So by this
So
way
by
I
this
can
way I can
extend my
extend my
definition of the
definition of the
function
function
to x equal
to
to
x
0,
equal to 0,
that point which
that
we are
point which we are
interested.
interested, okay?
So we
So we
satisfied our
satisfied
first
our
point
first point,
that the function
that
should
the
be
function should be
defined at that
defined at
particular
that
point.
particular point which we are interested to it.
Now the second
Now the
point is
second point
whether we
is
check
whether we check
the limiting
the
value
limiting
is
value
equal
is equal
to the
to
defined
the
value.
defined value.
Okay.
Okay.
And here what
And
we
here
see
what we
that
see that
we will
we will smartly
redefine our
redefine our
function.
function. We will
Smartly
smartly
redefine our
redefine our
function
function such
such
that
that we will
we
assign
will
that
assign
particular
that
new
particular new
definition as a
definition as
limiting
a
value,
limiting value,
so that we
so
can
that
say
we can
that
say that
my limiting
my
value
limiting value
is same
is same
as
as
that particular
that
defined
particular
function.
defined function.
I hope this
I
idea is
hope this
clear.
idea is clear, right?
And how
And how
we are able
we
to
are
remove
able
the
to remove the
discontinuity which was
discontinuity
there
which
earlier.
was there earlier.
Earlier we had
Earlier we had
discontinuity
discontinuity
because of the
because of the
definition of
definition
the
of the
function.
function, right?
So we
So
remove
we
that
remove that
discontinuity in the
discontinuity in the
definition
definition
by
by
explicitly
explicitly
redefining my
redefining
function.
my function,
By
by
concatenating
concatenating,
by
by
extending the
extending the
definition
definition of the
which is this,
function which is this, right? This is the extension of the, this is the new definition of the function. This was the old definition.
now you can see
Now you
over
can
here
see over here the
the domain
domain
is now full
is now
real
full real
line, right?
line, right?
That's the
So
difference.
that's the difference over
I
here.
hope this
I
idea is
hope this
clear.
idea
Can you
is
give me
clear.
one
Can you give
thumbs
me
up
one thumbs up
so that I can
so
move
that I
forward?
can move forward?
Okay.
Okay.
Today seems like
Today
many
seems
people
like
have
many people have
their
their
schedules.
schedules.
It's fine.
It's
We'll
fine.
continue.
Like we'll continue.
In this
In this
example,
example, what we
on
see that, for
the
example,
left hand
on the
side,
left hand side,
this is the kind
this
of
is the kind of
discontinuity we
discontinuity
cannot
we
remove
cannot remove
no
because
matter
no
what
matter what
redefinition of function
redefinition
you
of
do,
function you do,
you cannot
you
remove this
cannot remove
particular
this
jump.
particular jump.
Okay.
Okay.
So whenever you
So
see such
whenever you
kind of
see such kind of a
jumps,
jumps,
you
you
cannot
cannot
remove
remove
the
the
discontinuity.
discontinuity. And
This
this
is
is an
one of the
example of
continuity that
continuity,
cannot be removed.
discontinuity that cannot be removed.
Okay.
Okay.
Now right hand
Now
side
right
is
hand
one of
side
my
is one of
favorite
my favorite
example
example
when it comes to
when it comes to
continuity and
continuity and
discontinuity. When we try
discontinuity,
to
when we try to
characterize
characterize this
this definition
definition into
into
various
various
circumstances.
circumstances. On the right hand
On the
side,
right hand
if you
side,
see
if
very
we see
carefully,
very carefully,
this function is
this
known as a
function is known
dirichlet
as a
function.
dirichlet function.
And this function
And this
basically
function
tells you
basically
that
tells you that
whenever your
whenever
input
your input
is
is
irrational,
irrational,
you give me
you
output
give
as
me
zero.
output as 0.
Okay.
Okay.
And whenever your
And whenever
input
your input
is rational,
is rational,
you give
you
me
give me
an output
an output
as x,
as
the same
x, the
input
same
which you
input
gave
which
me.
you gave me.
So basically
So
over
basically
here
over
I'm
here
trying
I'm
to
trying to basically
segregate,
segregate,
which one is
which
real
one is
and
real,
which one is
sorry, which one is
irrational.
rational and which one is irrational.
So you can
So you
see
can see
have a
I can
plot
have a
of this.
plot of
I
this.
have
I
a
can
plot
have
of
a
this
plot of this
function
function
which is shown
which
over
is
here.
shown over here.
You can see all
You
those
can see
red
all those
dots.
red dots.
All those red
All
dots
those
which I
red
have drawn
dots
in a
which I have
plot
drawn in a plot
are
are
basically
basically
my rational
my
numbers.
rational numbers.
Okay.
Okay.
And all
And
those
all those
blue dots on
blue
the
dots
x
on the
axis,
x-axis,
these
these
are my
are my
irrational numbers.
irrational numbers.
And you can
And
see
you can
this
see this
function
function
is
is
discontinuous
discontinuous
at every
at
point.
every point.
This function is
This function is
discontinuous
discontinuous at every
except
point
one point.
except one point.
There is one
There is
special
one
point
special point
in which this
in
function
which
is
this function is
continuous.
continuous,
That
and
special
that
point
special
is
point
over
is
here at
over
the center.
here at the center.
You can see
You can see
at the
at the
center,
center,
no matter
no matter
my function
my
is
function
real
is
or
real,
my
so my
no matter my
no matter
function
my
is
function is
irrational or
irrational
rational,
or rational.
it is still very close to zero. I can always find an interval around here in which I can't see the difference in them, right? I can always find an interval here. I can always find an interval such that we have rational and irrational in that given interval. And if I take that interval around this zero, what do I see? all values tends to be 0, right? All values turns out to be 0. So what we see that the limiting value of the function at x equal to 0 is 0, and you can
And you
verify
can
that
verify that
from this graph
from this
in the
graph
center.
here itself in the center.
I hope you
I
understand
hope
this
you understand this
definition.
definition, why this function
Is
is
discontinuous
discontinuous at
at
every
every
point
point
except
except
x
x
equal
equal
to
to 0.
0. So this
Might be one of
might be
your
one of your
MCQ
MCQ question
question
in
in
your
your exam.
exam. This might be.
Okay, I'm just
Okay, I'm just
telling you why this
telling you why this question is important. The similar kind of
might
question you
come
might
in your
have. For
exam.
example, instead of x, they will
They write it as some
write it as
x
some
square
x
maybe,
square maybe.
right? Maybe instead
Right?
of
Maybe
x
instead of x, they will write as 1.
about
So what about
continuity.
continuity? Let's say
If instead of
if
x
instead of x,
there was some
there was
constant
some
value
constant value which is not 0, for example 1,
then you can say
then you
that
can say that
this function
this function
is not
is not
continuous at
continuous at
every
every
point.
point, even at the x equal to 0.
If I
Because
try to
if I
have a
try to
plot
have a
here,
plot here,
what do I see?
what
If
do
I
I
just
see? If I just try to,
dot
dot
all the
all the
rationals,
rationals,
then I would
then
see
I
this
would see
particular
this
dot.
particular dot.
Okay.
Okay.
And if I
And
try
if I try
to
to
plot all
plot
the
all the
irrationals,
irrationals,
I would see
I
this,
would
right?
see this, right?
And over
And
here you
over
can see
here,
there
you
are
can see there are
continuous
continuous
jumps.
jumps, right?
You can say there are
You can see
continuous
there are
jumps.
continuous jumps.
Each and every
Each and
point
every point,
there is a
there
continuous
is a
jump.
continuous jump, right?
Not continuous in
Not
the sense
continuous in the sense there is a,
I can always
I can
create
always create
an interval.
an interval.
I can always
I can
create an
always
interval
create an
in
interval
which I have
in
both
which I have
rationals
both
and
rationals
irrational.
and irrational.
And inside that
And inside
interval,
that interval,
all the points
all
have
the
a
points
different
have a
values.
different values, I mean to say.
So in this
So
case,
in this case, you don't have any limiting value,
even at the x
even
equal
at
to
the
0,
x equal to 0. But in
I
this
have
case, I have,
in the original
in the
problem
original problem, I
I
had
have limiting
a
value.
limiting value.
That's the difference.
That's the difference.
If you feel
If
that
you
this
feel
is
that this is repetitive to you,
repetitive,
let me know.
text
Text in the text
in the
box.
chat
In
box
the
you write
chat box,
down
you write
this is
down this is
repetitive. We can
repetitive.
move
We
forward.
can move forward. Okay.
Okay. In the next
In the
session,
next session,
we will try to
we will
discuss
try to
what is the
discuss what do we mean by
composition of function.
composition of function.
So in this
So
case,
in this case,
we will try
we
to
will try to see
what do we mean
what do
by
we mean by
fog of x?
fog of x,
What do we mean
what do
by
we
gof
mean
of
by
x?
gof of x.
You might have seen
You
this
might have seen
notation
this
in various
notation in
places.
various places,
So where the
so
fog
where
of
the
x
fog
is
of x is
basically
basically
composition of
composition of a two
two function.
function.
I can
I can
explain you
explain you
using this
using
diagram
this
over here.
diagram over here.
Okay, you can
Okay, you
see
can
from the
see from this
diagram.
diagram,
For example,
for
this is
example,
a
this is
domain
a domain
of a
of
function
a
f,
function f,
and this is a
and this is
range
a range
of a
of
function
a
f.
function f.
Now, what I
Now,
do,
what I do,
the range of
the
a
range of
function
a
of
function
x
of x
will
will
become a
become a
domain
domain
for the
for
function
the
g.
function g.
So this is
So
how I
this is how I
concatenate my
concatenate my
functions.
functions.
Okay, so you can
Okay, so you
say
can
that's the
say that's a
composition.
composition.
I can say it's a
I can say it's a
concatenation.
concatenation of two
So
functions.
you can
So
see
you can
this is
see
how
this
we are
is how we are
concatenating two
concatenating two
functions.
functions here.
So basically,
So
what
basically,
happens?
what
The
happens?
range of
The
one
range of
function
one
becomes a
function
domain for
becomes
the
a
second
domain for the
function.
second function.
Okay, so that's
Okay, so
how
that's how
we are able
we are
to
able
write
to
down
write down
this
this
composition function.
composition
You
function.
can see
And you can
from
see
here as
from
well.
here as well.
You can see the
You can see
function
the
takes an
function takes an
input as an
input
output
as
of
an
the
output of the
g function,
g function,
right?
right?
And in this
And in
case,
this case,
in this
in
case,
this case,
the range
the
of g
range of g
function
function
becomes the
becomes
domain
the
of the
domain of
f
the f
function,
function,
which
which
is
is this, right?
over here. You
Over
can
here,
see
you
this
can see this tree
from here,
from here.
the down
The down the this particular
path.
path.
So this is
So
what
this
your
is
f
what
of
your
g
f of g
definition is.
definition is.
The domain,
The domain,
this is the domain
this is
of the
the
g
domain of the
function,
g function,
which maps
which
you
maps you
from this
from this
set to this
set to this set,
and this set
and
is
this set
basically
is
the range
basically
of
the
g
range of g
function.
function.
And this
And this
particular further
particular
f,
further f,
you can
you
see
can
for
see
this
the for
function
this function f,
this becomes a
this becomes
domain,
a domain,
right?
right?
And this
And this
function
particular function will
take
take
you
you
from
from
this
this
set to
set
this set.
to this set.
And if you see
And
very
if you see very
carefully
carefully over here,
this is an
this is an
inverse
inverse
process.
process. You can say it's
Reverse
like a reverse
direction.
direction.
Okay,
Okay.
over here we
Over
see
here
that
we see that
the range
the
of
range of f function becomes a domain for the g function, which I have explained you in the first.
and in
And
general
in
this is
general,
very
this is very
important,
important. In general,
both
both
processes are not
processes are
equal.
not equal.
Okay,
Okay.
for
For
example here
example,
you have
here you
f of
have
g
f of g,
and over here
and
you
over
have
here you
g of
have
f.
g of f.
In general they
In
are not
general, they are
same,
not same.
they can be
They
different.
can be different.
Okay,
Okay.
but there is one
But there is
special
one
case
special case. Uh,
I would
I
like to
would
write
like to
down
write down if possible.
let me
Let
add a
me
page
add a
over here.
page over here. Okay.
This
this
something
something
called
called
as
as
inverse.
inverse of a function.
This is known
This
as
is known as
inverse.
inverse.
In case
In
any one
case
of you
any
don't
one
know
of you
about
don't
this,
know about this,
if
if
you
you
know,
know,
we
we
can
can
skip.
skip.
No issue in
Okay,
that.
no issue in that.
So what this
So what this
basically
basically
inverse of function
inverse of
means
function
is
means. So the
definition of
definition of the inverse of function is that
if you
if
give
you give
an input
an input
as a
as
function
a
f of
function f
x,
of x,
what do I see?
what do I see?
I see
I
as an
see
output
as an
x.
output x.
You can
So
see
you can see here,
you
right?
can see
You
from
can
here
see from
that
here that
one of my
one of
function
my
is f
function
of
is f
x.
of x.
My another
My
function
another
is
function is
g of
basically
x.
g of x,
But
but
g
g
of
of
x is
x is
taken as
taken
an
as an
inverse
inverse
function of
function of
fx.
fx.
And if I try
And
to
if I try
compose
to
it,
compose it,
this
this
particular
particular
thing,
thing,
which is
which is
basically right.
basically right.
See, this is
See,
not
this is
actually
not
zero
actually
or o,
zero
which
or
is
o, which is
basically
basically
a very
a
small
very
circle.
small circle,
And this very
and
small
this very
circle
small circle
represents that I'm
represents that I am
composing
composing
two of my
two of
function,
my function,
which is
which
defined
is
in this way.
defined in this way. Okay,
Which is
which
defined
is
in this way.
defined in this way.
So this is the
So this is a
definition
definition.
and
This is just
notation.
notation and definition.
And over
And
here,
over here, what we see that
this
this turns out to be
f of
f of
f inverse
f
of
inverse
x,
of x,
and
and
at the end we
at
have
the end we
x.
have x.
Please,
Please, I
please
repeat, please
don't cancel
don't
this.
cancel this.
This is not
This is
a
not a
algebraic thing.
algebraic
This is
thing.
a
Okay, this is a
definition.
definition.
This is not
This
like
is
a
not like a
cancel.
cancel thing.
This
This
is
is
a
a
definition.
definition.
Okay.
Okay,
What this
basically what this
definition tells you
definition
that
tells you that
if you
if you
have a
have a
process,
process,
you have done a
you have done a
process.
process.
For
For
example,
example,
over here
over
to here.
here to here.
So this is
So
your
this
f.
is your f.
This is a
This is
process.
a process.
So what is the
So
inverse
what is the
process?
inverse process will be?
So it will
So
map you
it will
from
map you
this
from
to this,
this
right?
to this,
For
right?
example,
For
this is the
example, this
domain
was a
for this
domain
f.
for this f.
So this will
So
be
this will be
the range for
the
f.
range for f.
But now what
But now
happened?
what happened? The
The range
range
of your
of
function
your
will become
function will
domain.
become domain.
Domain for the
Domain for
f
the
inverse,
f
and this will
inverse, and
become
this
the
will
range
become the range
of f
of
inverse.
f inverse.
So what kind
So
of
what kind
property
of
do we need
property
in
do
order
we
to
need in
have
order to
this
have this
inverse
inverse
existence
existence
of
of
this
this
inverse?
inverse? Can anyone
Guess. Can
guess?
anyone
Can anyone
write it for me
write for me
in text
in
box?
text box?
Like what
Like
important
what
property
important
is needed
property
in
is
order to
needed
have
in
this
order to have this
existence of
existence
inverse?
of inverse?
Not every
Not
function
every
is
function is
invertible,
invertible,
I would say.
I mean to say.
Invertible in the
Invertible
sense
in
the
the sense the
existence of this
existence of this
inverse.
inverse.
Not any
Not
function
any
can be
function
written
can
down
be
as an
written down as
inverse.
an inverse.
There are very
There are very
special
special
class of
class
functions
of functions
which
which
can
can
be written
be
down as an
written down as
inverse,
an
and for
inverse,
which
and
this
for which
inverse
this
exists.
inverse exists.
And we are
And
always
we are always
interested
interested in
in
this
this inverse
inverse
so
so
that we
that we
can
can
understand. We can
understand,
do
we
always
can do
back
always this
engineering
back
process
engineering process
to understand
to
what this
understand what
function
this
gives.
function gives.
Can anyone
Can anyone
write down
write
what is
down
that
what is
function?
that
What is the
function? What is that
important property
important property
of the
of
function
the
we need
function we need
in
in
order
order
to
to
existence
the
of this
existence of
inverse,
this inverse,
right?
right?
You just try to
You
use
just
the
try to
usual
use the usual
definition of
definition
domain
of
and range,
domain and range, okay?
so that you
So
can
that you can
tell
tell
me
me
what's happening
what's
here.
happening here.
By the time you
By the
write
time you
down the
write
answer
down
in
the
the text
answer in
box,
the
I will
text
write
box, I
down
will
over
write
here.
down over here.
The first
The
thing we
first
need
thing we
is
need
that
is that
the function
the
must
function
be
must be
one-to-one
one to
mapping.
one mapping, right?
There should
There
be
should be one to one mapping.
and the
And
second
the
thing
second thing which we want
is that
is that
function should
function
be
should be
an onto
an
function.
onto function.
Onto
Onto
function. It
function.
should be an
It should be an
onto mapping.
onto mapping.
People write it as
People write it as
onto,
onto
or
mapping, or
sometimes people
sometimes
write
like people write
surjective
surjective
mapping.
mapping.
Surjective
Surjective
mapping.
mapping.
In this
In
case,
this case,
people also
people also
often
often
try
try
to
to
write
write
as one to
as
one
one to one
or as
or as
injective mapping.
injective mapping.
So
So in order
in order
to
to have this
have
inverse
this
function,
inverse function,
we need
we
both of
need
this
both of
property.
this property.
So from
So
word
from
call
word
as one
call
to
as
one, you
one to
can
one, you can
understand
understand
for
for
each
each
variable
variable
in this
in
domain
this domain there
there is
is a unique
image,
image,
a
a
unique
unique
mapping.
mapping.
Okay,
Okay,
like for
like for
example over
example
here,
over here,
and let's
and
say
let's
there's
say
another
there's
point
another
over
point
here.
over
So we
here,
have a
so we have
unique
a
mapping
unique mapping
here to
we
here.
here
So
to
this is
here.
called
So this is what
one to
called
one
one to
mapping.
one mapping.
One
One
element of this
element of
domain
this
is
domain
mapped
is mapped
to the
to
another
the
element
another element
of the set,
of the set,
and we call that
and we
set as
call
a
that
range.
set as a range. Okay,
So this is
so
what
this is what
very
this is
trivial to
very
understand
trivial to
what is
understand
this.
what is this.
Maybe many of
Maybe
you
many of you
haven't
haven't got the idea of this on toward the subjective
mapping,
subjective
subjective
mapping is
mapping,
basically
tells you
tells
that
you that
when the
when the
range
range
of
of
function
function
is equal
is
to the
equal to the
codomain.
codomain.
Since this is a
Since
very
this is a
technical
very
word,
technical word,
if you are not
if you are not
understanding
understanding
this
this
language,
language,
it's
it's
okay.
okay.
I'll
I'll
tell
tell
you
you
what
what
this
this
means.
means.
So this
So this
basically tells you
basically
that
tells you that
um,
um,
if we consider
if we
any
consider
element
any element
in this particular
in this particular
set
set
range
range
of
of
this
this
function,
function,
there always
there
exists
always
a
exists
unique
a unique inverse map, a unique map
in the domain
in the
of this
domain
function.
of this function. There is always exists a unique,
Always.
always.
So we can
So
see this
you can see
as
this as inverse of inverse
kind of
kind of one mapping. So this can be seen as
one to one
one to one
mapping.
mapping. In the sense of reverse.
Okay.
Okay.
I hope the
I
ideas are
hope the
clear.
idea this all these ideas are clear to you. I just need one thumbs up, okay,
So that I
so
can
that I
move
can
forward,
move forward,
so that I can
so
discuss.
that I can discuss. Yeah.
I
Okay.
hope these
I
ideas are
hope these
clear.
ideas are clear to you.
Okay.
Okay.
Now the
So
next
now the
idea is
next
that.
idea is that.
My
So
claim
my
is
claim
the
is
main
so the
claim of
main
this
claim of
whole
this whole
discussion hmm, is that whenever you have a composition of function and that turns out to be continuous,
continuous,
right?
right?
If you have a
If you have a
composition of function
composition of
and
function
that turns
and
out to
that
be
turns out to be
continuous in the real
continuous in the
variable,
real variable,
then the claim
then
is
the
that
claim is
the
that
function
the
is
function is
continuous in the range of
continuous in
G.
the range of G.
Why?
Why?
Because
Because
if I write
if I write
if I write
if I write
that
that there
this
is
function
this function
is
is
continuous on R,
continuous on R,
that means
that
the
means the
domain
domain
of this
of this
particular
particular
composition
composition
is actually
is
equal to the
actually
range,
equal to
right?
the range, right?
That's why I'm saying
That's
it
why
is
I'm saying it is
continuous over all
continuous over
real
all real
variables.
variables.
That means
That means
if I talk
if
about
I
the
talk about
range
the range
of
of
G function,
G function,
that will be
that will
real
be
number,
real number, right?
because
Because
in this
in
case
this case,
the input
the
of the
input of the f
function
function is basically the range of
G
the
function.
G function, right?
And if I'm
And
saying
if
that
I'm saying that
the
the
composition of
composition of
FOG composition
composition
is
is
continuous on R,
continuous on R, that means
the domain
the
of this
domain of this
composition
composition is
is basically
basically
R.
R.
And
And
since I know
since
that
I know that the domain of this function is basically what the range of the G,
I
right?
can
So I
conclude
can
that the
conclude that
function
the
is
function is continuous in the range of
G.
G.
So this is
So this
important
is
because
important because over earlier
I had the
I had
information
the
about the
information about the
composition
composition
function.
function.
I had the
I had the
information about the
information about the
composition,
composition,
but I didn't
but
have
I
any
didn't had any
information about
information about
individual.
individual.
Whether
Whether
G is
G is
continuous,
continuous,
F is
F is
continuous.
continuous.
So from this
So from this
statement,
statement,
I'm able
I'm
to
able to
comment. I'm
comment.
able to
I'm able to
conclude
conclude
that the
that the
function is
function is
continuous,
continuous,
but in the
but
range
in
of
the
G.
range of G.
But in the
But
range
in
of
the range of
G.
G.
Okay.
Okay.
Since
And
the range
since
of
the range of
G
G
is R,
is R,
then we can say
then we
the
can say
function
the
is
function is
continuous
continuous in R.
and R is
And
basically
R is
the
basically
real
the
line.
real line.
I hope this
I
idea is
hope this
clear.
idea
This
is
is
clear.
not
This is
a
not a
confusing topic.
confusing topic to you, right?
This can be
This
one of
can be
your
one of your
MCQ.
MCQ.
For example,
For
they will
example,
write
they
down
will
this
write
as
down
a
this as a
question,
question,
and
and there will be
points. There will be
points,
many
many
points. For
points.
example,
For example, A point will be
F is
F is
continuous in such a
continuous in
way,
such a way,
and G is
and G is
continuous in
continuous in
such a
such a
way.
way.
So
So
you
you
have
have
to
to
select
select
which
which
statement is correct.
statement is correct. Okay.
Okay.
So they will give you four statements. You have to choose the correct
So
statement. So this can be
this
one
can
of
be one
your
MCQ type of
MCQ type
question.
of question.
Now the next
Now the
point which
next
I want
point
to
which I want to
discuss
discuss
is that
is
what
that
happens
what
when we
happens
have
when we have
a very
a very
closed
closed
domain.
domain.
Okay, closed
Okay,
in the
closed
sense
in the
when
sense
you have an
when you have
interval.
an interval.
Earlier case,
Earlier case,
we had
we
this
had
kind of
this kind of
function
a function
where we
where we
assumed
assumed
in our
in our
discussion
discussion we assumed everywhere
that the
that
function
the
is
function is
defined over
defined over
range,
range,
defined over
sorry,
real
defined over
number,
real number,
and
and real number is getting mapped to another real number in some fashion,
and that fashion
and
is
that fashion
described
is
by this
described by this f
function.
function. Okay.
Now what
Now what happens when we have
an interval,
an interval,
and this
and
interval
this
is getting
interval is
mapped to a
getting
line
mapped to a line
because of this
because
function.
of this function. Okay.
So how
So
do we
how do
understand
we
this
understand this
situation?
situation?
And
And
one important
one
point we
important
need to
point we
understand
need to understand
that whenever we
that
have
whenever
this
we have
interval
this interval
and we talk
and
about
we
these
talk
boundary
about these
points, for
boundary points,
example
for
A and
example
B,
A and B,
these are actually
these
the
are
boundary
actually the
points of
boundary
this
points of
interval.
this interval, right?
So in the case
So
of
in the case
boundary,
of boundary, we
we
have
have
only
one
one kind
continuity.
of a continuity.
That is called
That
as
is called as
left
left
continuity
continuity
for
for
the
the
left
left hand
boundary.
boundary.
We have
We
right
have right
continuity
continuity
for the right
for the
boundary.
right boundary.
We don't have
We
something
don't
called
have
as
something called as
absolute
absolute
continuity
continuity
at boundary
at the
points.
boundary
At the
points.
boundary
At the
points, we
boundary
have
points, we have a definition something called as left continuity and the right continuity.
since we
Since
don't have
we
any
don't have any
information about
information about
the
the
left and right
left
of
and
these
right of
various
the various
boundaries.
boundaries, okay?
I hope this
I
idea is
hope this
clear
idea
and
is
not
clear and
confusing
not
to all.
confusing to all.
So
So
basically,
basically, what this
now
theorems,
the
now
following
the
theorem
following
tells you,
theorem tells you.
the following
The
theorem
following
tells you is
theorem
very
tells you is
important
very
theorem.
important theorem.
I will
I
mark
will
this as
mark
very
this.
important. To me, this theorem is very important because this theory basically tells you that whenever you have a function and it is defined in such a way, and let's say at a given point, if you take the value, if you try to compute the value of the function at a given x equal to a, the value of the function turns out to be positive. So my claim is
So my
that
claim is
there
that
always
there always
exists an interval.
exists an interval.
There always
There
exists an
always
interval
exists an
at the
interval at the
x-axis
x-axis
such that
such that
the
the
function is
function is
positive.
positive.
So if I'm
So
able
if
to
I'm able to
compute a
compute
value of
a
a
value of
function
a function
at a given
at a
point,
given point,
then that
then
means
that
I
means
always
I
can
always
find
can find
some values
some
of x,
values of x,
some
some
other
other
values
values
of
of
x
x
for which the
for
function
which
is
the function is
positive.
positive.
Over
Right?
here
Over here,
basically
this
tells you
basically
that
tells you
I
that I
can
can
always
always
find
find some
set of x's,
set
set of
of
x
x
values
values
for which if
for
I
which
try
if
to
I try to
compute
compute
or try to
or try to
calculate
calculate what is the value of the
the
function
function
turns out
turns
to
out
be
to be
positive.
positive. And this
And this
definition is
definition
also
is
true
also true
in the cases
in
of
the cases
negatives.
of negatives.
Just
Okay,
replace this
just
all with
replace
the
this all
negatives.
with the negatives.
This theorem is
So this
also
theorem
true.
is also true.
And you can see
And
this
you can
theorem
see this theorem
graphically over here.
graphically over here.
Here we can see
Here
that
we
this
can
is a
see that
function
this is a
f,
function f
and it is
and it
defined
is
in this
defined in
black
this
curve,
black curve,
okay, which I have
okay,
traced
which I have
using a
traced
laser.
using a laser.
So what do I see
So
that
what do
there
I
is
see
some
that there is
grid
some
point over
grid
here,
point over here,
okay,
okay,
and there
and
is
there
a
is a
orange points
orange
over here,
points over here, and there is the red points over here.
and you can see
And you can see
accordingly
accordingly I have marked
the
the
intervals.
intervals.
Okay, so
Okay,
basically
so
the green
basically the
point
green point
is the
is
given
the given
information
information
over here.
over here which is given to you.
Now what I'm
Now
trying
what
to
I'm trying to
basically do over
basically
here,
do here,
I'm trying to
I'm trying to
basically build an
basically build
interval
an interval
around this
around this
point, which I
point
know.
which I
Using
know
some
this using some
experiment. I know
experiment,
this.
I know this.
So what do I
So
see
what do
that
I see that
the values
the
inside
values
this
inside
interval,
this interval,
and if I try
and
to
if I try to
calculate the value
calculate
of
the
the
value
function
of the
in that
function in
interval,
that interval,
which get
which
mapped
gets
over
maps
here,
over here,
which gets
which
mapped
gets
over here,
mapped over here,
they all
they all
values
values
are
are
positive values.
positive values.
They are not the
They are
negative
not the
values.
negative values. Okay.
And these red
And
dots
these
are
red dots are
basically
basically the roots.
roots. What do we
Roots,
mean by
what do we
root?
mean by root of an equation?
Root of an
Root of an
equation is
equation is
basically
they
a
are
special
basically a
point
special point
at which
at which
the
the
value of the
value
function
of the
changes.
function changes.
For example,
For
from
example,
positive to
positive to
negative.
negative. In this case here it changes from negative to positive.
And in this
And
case
in
it
this
changes
case
from
it
positive to negative. So here the red dot basically represents the roots of the function, and over here the orange dot represents basically the boundary of that interval which we defined at the point A, for which we know already the function value is positive. I can always create an interval such that around this point which has a positive value. If you want to see the situation over here, I have zoomed out, which illustrates the same
illustrates
idea.
the same idea.
I hope this idea
I
is
hope this
clear to
idea
you.
is
You can
clear to you. You
give me
can
thumbs
give
ups
me a thumbs up
so we can move
so we
forward.
can move forward.
Is this clear to
Is
you?
this clear to you?
Or is this boring to
Or is
you?
this boring to
Or
you?
is this boring?
Or is this boring little?
We can move forward.
We can move forward, okay?
So the next
So the next
part
part
we're going to
we're
discuss
going to
is
discuss is something called as
intermediate
intermediate
value
value theorem,
which we also call
which
as
we also call
IVT.
as IVT.
And this is very
And this is
important
very
because
important because
there are various
there are
instances
various instances
which we want to
which we
know
want to know
whether the function
whether
have
the function
changed
have
value or
changed
not.
value or not.
Okay,
Okay,
whether there exists
whether
a
there
root or
exists a
not.
root or not.
So,
So,
for
for
example,
example,
the motivation, the main motivation of this particular discussion is that uh, root. What are the roots of the function? Do roots exist? We want to
we
answer
want
that
to
kind of
answer
a
that kind of
questions,
a questions,
and these
and
questions
these
can be
questions
answered
can be
using
answered using
intermediate
intermediate
value
value
theorem.
theorem.
Okay,
Okay,
but
but
the question
the
that the
question
root
that the root
exists,
exists,
this question can
this
also
question
be
can also be
further
further
extended
extended
to any
to
value,
any value,
not just
not just
fx equal to
fx
0.
equal to 0.
You can also
You can
ask,
also ask,
I just want
I
to
just
know the
want to
values
know
of those
those
values
values
of
of
x
x
which
for
gives
which
me
this
the value
function
L.
gives me value L.
We can also
We can
answer
also
these
answer these
questions.
questions.
See, many
See,
times
many times
you were able to
you were able
calculate
to
the values
calculate the
of
values
x,
of x,
just by
just
doing
by
simple
doing
algebraic
simple algebraic
calculations that what
calculation
you have
that what we
did
have did
in your school
in your school
and in your
and
11th
in your
12th,
11 12.
because the
Because
questions
the
which were
questions which
designed
were designed
in your
in
textbooks,
your textbooks,
those questions
those
were very
questions were
simple.
very simple.
You can
You can do all the rearrangements, you can do the
algebraic
algebraic
manipulations
manipulation in
to
order to
get
get
the value of
the
x
value
equal
of
to 0.
so-called x equal to 0.
But there are
But there are
various
various
instances
instances
where it's
where
very
it's very
hard to
hard
find
to find
the
the
values
values
of the
of
x.
the
I can
x.
give you
I
one
can give you one
example.
example.
This would be
This
very
would be
interesting
very
to
interesting
discuss.
to discuss.
For example,
For example,
um,
um,
e to the
e
power
to the
minus
power
x
minus x
plus
plus
x
x
equal to 0.
equal to 0.
So,
So,
I just want to
I
know
just
how
want to
many
know
roots
how many
exist.
roots exist.
So, do we
So,
have
do we have one root?
do we have
Do we have
two roots?
two roots?
Do we
Do
have
we have
multiple roots?
multiple roots?
Or we don't
Or
have
we
any
don't
roots?
have any roots?
For example,
So,
this we
example,
have
this
this
we have
question
this question
to us,
to us.
and
And it
out
turns
that
out that just
simple
doing
algebraic
simple algebraic
manipulation you
manipulation,
cannot
you
just
cannot
solve the
just
answer
solve the answer
and get the
and
answer.
get the answer, right?
So,
So,
in order to
in
get the
order to get the
solution for
solution
this,
for this,
we are
we are
dependent
dependent
on
on
different
different
type of
type
tools
of
which are
tools
known as
which are known as
numerical
numerical
methods.
methods.
Using numerical
Using numerical
methods, you can
methods, you can
estimate
estimate
roots.
roots.
We can
You
estimate
can
roots.
estimate roots.
First thing, you can
First thing, you
estimate
can
the roots
estimate
do
the roots
exist.
do exist.
Second thing,
Second
you
thing,
can
you can
calculate. There
calculate.
is a
There
proper
is a proper
procedure
procedure
you can
you can
calculate.
calculate.
Okay.
Okay.
So,
So,
why do we need
why
this
do we need
numerical
this
methods?
numerical methods?
By
Because
using
by
hand,
using hand, because just using pen and paper,
just by doing
just by
simple
doing simple
numerical
numerical
manipulations,
manipulations,
you were
you
unable
were
to
unable
calculate
to calculate
the answer.
the answer.
And my quick
And my
answer
quick
for
answer
this
for this
is that we don't
is
have
that we
any
don't have
roots.
any roots.
And how can I
And
say
how
that?
can I say that?
Simple,
Simple,
by just drawing
by just drawing the graph, I can say
we
this.
don't have
We
any
don't
roots
have any roots
because this
because this
equation can be
equation
written
can
as
be
e to
written
the
as
power
e to the
minus
power
x
minus
equal to
x
the
equal to
minus
the
x.
minus x.
We know
And
that
we know that
we,
we
we clearly know that.
clearly know that.
See, this is
See,
your
this is your
y equal to
y equal
minus
to
x.
minus x.
This is the
This
line.
is the line, okay?
See, you can
See,
see
you can
there are
see
two
there
lines.
are two lines, right?
One line is
One line is
e to the
basically
power
e to the
minus
power
x.
minus
Another
x.
is
Another line is
y equal to
y
minus
equal
x.
to minus
And
x.
if these two
And
lines
if these two
intersect,
lines intersect,
the point of
the point of
intersection is your
intersection is
root.
your root.
The point of
The point of
intersection is your
intersection
answer
is your answer
because
because
that particular
that
point
particular point
basically
basically
satisfies
satisfies
both.
both, right?
Let me write down,
Let me
then you
write
will
down, then you will
understand what I'm
understand what
trying
I'm
to say.
trying to say here.
And this is
And
your
this is your
e to the
e
power
to the
minus
power
x. And
minus
you can
x.
see
And you
these
can
two
see
lines
these two
don't
lines
intersect.
don't intersect.
You can see
You
this
can see this
red line
red line
and this
and
blue
this
line.
blue line, they don't intersect.
Actually, what
Actually,
happens?
what happens is red line becomes an asymptote
For this e to
for
the
this
power
e to the power
minus
minus
x
x
at
at
infinity.
infinity somewhere.
Okay.
Okay.
So what do we
So
see
what do
that?
we see that?
But they never
But they
touch.
never touch, right? They never touch exactly. They never intersect.
So we don't
So
have
we
any
don't have
roots
any roots
over here.
over here.
That's the idea.
That's the idea.
So roots don't
So roots
exist
don't
in this
exist
case.
in this case. I was able to claim this
using graph.
using graph.
Just using
Just
graph.
using
I
graph.
hope
I
everybody
hope
understood
everybody
this idea.
understood this idea, right?
Give
Can
me
anyone give me a thumbs up
everybody
that
understood
everybody understood
this idea.
this idea?
Yeah, using the
Yeah,
graph
using
you
the
can
graph you
estimate
can
the root
estimate the
exists
root
or don't
exists or
exist.
don't
You just
exist.
have to
You just have to
calculate
calculate
the number of
the number of
intersections
intersections,
because that
because that
intersection
intersection
point
point will
will be
be
the
the
point
point
which
which will satisfy this
will this
and this
together.
together.
And this is what
And
this
this is what this
equality tells you.
equality tells
I
you.
want a
I want a
I
situation,
want a
I want a
situation
situation, and I want a
in which
value for which
these two
these
functions
two
is same.
function is same.
This is what
This is what this
equation can
equation
be
can be
reframed.
reframed into it.
Just
And
using the
just using the
plots,
plots,
I figured
I
out
figured out
there are no
there are
roots.
no roads.
But you might have a
But you might have a
situation
situation
you are
you
unable
are
to
unable to
do this.
do this.
Let's
Let's
say
say
you want very
you
quick
want very
answer.
quick answer.
You cannot
You
wait for the
cannot wait for the
numerical
numerical
simulations to do.
simulations to do.
You cannot
You cannot,
let's say
you
you
don't,
don't
let's
have
say
a
you don't have
knowledge
a
for this
knowledge for this
numerical method.
numerical method.
And let's say
And
you
let's
are
say you
unable
are
to
unable to
have a plot.
have a plot.
In this case I
In
had
this
the
case, I
very
had the
easy
very
functions.
easy functions.
But most of the
But
time
most of the time, you might be having very
complicated
complicated
function.
function,
And it's very
and it's
hard to
very hard to
imagine what
imagine
kind of
what kind
plot
of
it is.
plot it is.
Okay.
Okay,
So this
so let's
idea
say
is
this idea is
not in your
not in
option.
your option.
This is also
This
not
is
in your
also not
option.
in your option.
So is there
So, is
any
there
other
any
way
other
to
way to
figure out
figure out
whether do
whether
roots
do roots
exist or
exist
not?
or not?
So the
So
answer
the
is
answer is
this
this
intermediate value
intermediate
theorem.
value
I
theorem.
hope
I
everybody
hope
got the
everybody got the
motivation behind this
motivation behind this
intermediate value
intermediate
theorem.
value theorem.
Because
So
intermediate
this
value
intermediate
theorem,
value theorem,
as
as a
a name
name
itself
itself, it tells you,
it
it
estimates an
estimates an
intermediate value
intermediate value
between an
between an
interval.
interval.
Okay,
Okay,
for
for example, in this particular
graph,
graph,
let's say there's a
let's say there's a
function.
function which is defined.
I don't know the
I don't know the
trajectory.
trajectory.
Let's say I
Let's
know a
say I know
function.
a function.
Let's say I know
Let's say
what
I
is the
know what is
function
the
f of
function f
x
of
equal to
x equal to
something very
something very
complicated,
complicated,
and
and I don't know
the graph.
the graph.
I don't know
I
how the
don't know
function
how the
looks.
function looks,
But I
but
for
for
sure I do
sure I
know
do know that
at the x
at
equal to
x
where the
equal to where the
function value
function value
is
is
positive, the
positive,
value of the
the value
function
of
is
the function is
positive.
positive.
At some
At
other
some
point,
other
which is
point,
x
which
equal
is
to
x
b,
equal to b,
the value of the
the value
function
of the
is
function
negative.
is negative.
I just know
I just know this 2 point,
nothing more.
nothing more.
I just
And I just want to
estimate.
estimate.
I just want
I
to
just want to
estimate
estimate
the
the
intermediate values.
intermediate values.
And the
And
condition
the
behind this
condition behind, and the assumption behind this assumption is that,
and the
and
condition
the
behind this
condition behind this
estimation is that
estimation is that
we want our
we
function
want
to
a
be
function to be
continuous.
continuous.
Okay.
Okay, and
If you
if
know
you know
these
these
two
two
things,
things,
the
the
first,
first,
the function is
the function is
continuous
continuous at x
between a
equal to
and
a
b,
and s equal to b,
and second,
and the second,
we know
we
they
know
have
they have
opposite
opposite
values.
values.
This basically
This
tells you
basically
that
tells you that
both have
both have opposite
opposite
value.
values.
This
This takes
basically
care of
takes
both
care
the
of both
cases.
the cases, right?
When f of a is
When f of a
negative
is negative and
and
f
f
of
of b
b
is
is
positive.
positive.
This
This is more general way to write down things,
you
right?
might
Because
also
you
have
might
a
also have a
situation
situation in which
this
this
over
is
here
over here
and
and this is over here
you might
somewhere.
have an
You might
opposite
have an
situation.
opposite situation.
So that case
So
is
that
also
case is
taken
also
care
taken care inside this condition.
so it's always
So it's
nice
always
to
nice to
understand
understand
how
how
do
do
we
we
write
write
these equations.
these equations, right?
I hope everybody
I hope
understand
everybody
how do
understand
we
how
write
do
this
we write
equation
this equation,
because this
because
just
this
tells
just
you
tells you,
just try to
just
get the
try to
idea
get the
what
idea
this
what this
equation is
equation
that
tells you. The idea is that
the
the
sign of
sign of f of a and f of
is
b is
opposite
opposite,
and that's
and
what the
that's
more
what the more
fundamental thing
fundamental
is.
thing is.
Okay.
Okay,
You might have a
you might have a
situation in
situation
which
in
f
which
of a
f of
is
a is
positive, f of
positive,
b
f
is
of b is
negative,
negative, and vice versa.
we don't care
We don't
about
care about
that idea.
that idea.
We care more
We care
about
more
that
about that
they have a
they have
opposite
a
sign.
opposite sign.
Okay.
Okay,
And
and
and the claim
and the
is
claim
whenever
is
you have
whenever
such
you have such
situation,
situation,
the theorem
the
tells you
theorem tells you that
there
there
exists
exists
a
a
particular value of
particular
a
value of
function,
a function,
a value of
a
a
value
function
of a function
which is said to
which is
be a
said to
root.
be a root.
There exists a
There
root in
exists a
between.
root in between.
So you might have
So
a
you might have
situation
a
in which
situation in which
you might have
you might have this
green color
green
line
color line
as to be your
as to be
function.
your function.
You might have a
You might have a
situation in which
situation
this
in
red
which
color
this red color
line
line
is your
is your
answer.
answer.
It can be
It
both.
can be both, right? It
It can
can
be
be
any
any
possibility. But the
possibility.
idea
But
is
the
that
idea is that
there
there
exists a
exists
point
a point
which
which
cut this
cut
x
this
axis
x-axis
at least
at
once.
least once.
That's the idea.
That's the idea.
At least once.
At least
You
once.
cannot
You
comment
cannot
about the
comment
number
about
of
the number
routes,
of routes,
but you can
but you
for
can
sure
for
say
sure
that
say
if
that if these
these
two
conditions
conditions are
is fulfilled
is
by a
fulfilled
function,
by a function,
then I can
then
say
I can say
there
there
exists a
exists a
particular point
particular point
in which
at
the
which
function
the
cuts
function cuts
the
the x-axis at least once.
So this
So
this is what
this is
basically
what
tells you
basically
that
tells
there
you that
exists
there
a root
exists a root
in that
in
particular
that
interval.
in this interval.
Let's say in this particular
X equal to and x equal to b, there exists a root
cut to
which
this
cut to this
axis.
x-axis.
And I think And I
And I
can
can
give
give
you
you
two
two
examples.
examples here.
Here we have two
Here we
quick
have two
examples.
quick examples.
Over here we
Over
have
here
this
we have
function
this function
fx,
fx,
and here we have
and
the
here we
function
have
h of
function
x.
h of x.
And what do we
And
see
what do
that?
we see that?
For
For
example,
example,
in this h of
in
x
this h of
case,
x case,
you can see
you
here
can see here
there is a boundary
there is a
value which
boundary
has a
value which
negative
has a
value,
negative value,
and over
and
here
over
we have
here
another
we have
boundary
another
value
boundary value
which is
which
positive.
is positive.
And if I try to calculate over here, this condition is satisfied, that the both value should be negative, right? I mean relative value should be negative. But in this case, but in this h of x case, this function is discontinuous. So it doesn't satisfy one of the assumptions behind this intermediate value theorem, right? So we cannot
So we cannot
apply over
apply
here the
over here
intermediate
the
value theorem.
intermediate value theorem.
So every
So
time when you're
every
trying
time
to
when you're
use
trying to
any tool,
use your any
whenever
tool,
you're trying to
whenever
use
you
any
try to
tool,
use any tool,
first check
first check
whether this tool
whether
can
this
be
tool can be
applicable or not in
applicable
this
or not in
situation.
this situation.
Because in this
Because in this particular
particular
function
function
like
like hx,
hx,
you cannot
you
apply
cannot apply intermediate
because
value
it
theorem
doesn't
because it doesn't
satisfy
satisfy the
basic criteria
basic
that the
criteria
function
that the
should be
function should be
continuous. It doesn't
continuous. It
satisfy
doesn't
this.
satisfy this.
So you cannot apply over here intermediate value theorem, even though you don't have any root in this case.
In this
If you
case,
check, hfx
if you
don't have
check
any root,
hfx don't have
even
any
though
root,
the values
even
have
though
the
the
boundary
values
points are
at
opposite.
the boundary points are opposite.
So that's the idea.
So that's the idea.
And similarly, we can
And
also
similarly,
see
we
the
can
same
also see the
situation
same
over here.
situation over here.
If you see
If
that
you see
at x
that
equal to
at x
0,
equal to 0, we have
a positive
a
value,
positive
at x
value.
equal
At
to
x
1
equal to
we have
1, we have
negative
negative
value,
value.
and
And
you can see
you
there is
can
no
see there
root
is no root
in the graph
in
at
the
least.
graph. At least you
You
can
can
see that. You
confirm
can
that
confirm that from the graph.
there is no
There
root.
is no root.
And
And
this
this
sounds
sounds
like we
like
have
we
done
have
something
done
wrong.
something wrong.
The idea is
And the
that you
idea is
cannot
that you
apply
cannot apply
intermediate
intermediate
value
value
theorem
theorem over here.
just because the
Just
function
because
is
the function is
not
again is not
continuous.
continuous.
It doesn't
It
satisfy.
doesn't satisfy. So don't forget this, okay? So
Whenever
whenever
you have a
you have a
situation
situation
and it talks
and it
about
talks
the
about the
existence
existence
of
of
the
the
root,
root and all,
you have to
so you have
very
to
careful
very
whether
careful
this
whether this
condition
thing is whether
is
this thing is
satisfied or not.
satisfied or
You might be in hurry just by looking this, you conclude there is exist a root, but you have to check and verify is there any discontinuity in between, because you might have a situation over here the discontinuity basically helps you to slip out, to without cut this x-axis you can slip away right from here to here without even cutting out the x-axis. So that's why discontinuity can be very problematic to generalize your definitions. I hope this idea
I
is
hope
clear.
this idea
Now
is
we will
clear.
go to
Now
the
we will
next
go to
point.
the next point.
And
And
the next point
the
is
next point is
we'll talk about a
we'll talk
theorem
about a theorem
which is defined
which
in
is
an
defined
interval
in an interval
and which
and which
maps this
maps
interval
this interval
to a real
to a
variable.
real variable.
And we
And we
assume
assume
that this
that this
function
function
is a
is
constant
a
function.
constant function.
So if you
So
want to
if you
see
want to
that
see
in a
that
graph,
in a graph,
let's say
let's say
this is your
this is
function,
your function,
this is your
this is
x,
your x,
and let's say we
and
have
let's say we
interval
have
x
interval
equal to
x
a
equal to a, and we
and
have
x equal
interval
to
x
b.
equal to b right over here.
So you might have
So
a
you might have a
situation in which
situation
the
in which
function
the
takes a
function takes a
constant value in
constant
between.
value in between.
That's it.
That's it.
Sub constant
Sub
value.
constant
Let's say
value.
c,
Let's just see.
and I will
And
mark
I'll
it as
mark it
solid
as solid
because these
because
boundary
these
points
boundary
are
points are
included in the
included in the
definition. How do
definition.
I
How
see
do I
that?
see that?
Because of
Because
this
of this
square bracket.
square bracket.
This square
This
bracket
square
tells you
bracket
that
tells you that
a and b
A
point
and
are
B point
included.
are
They are
included.
not
They are not
excluded.
excluded. Okay.
And
And
over here,
over
what we
here,
see
what we
that
see that this theorem,
this theorem
this
basically
theorem
tells you
basically
that
tells you that
let
let
c,
C,
like over here,
like over here,
so there
so
exists a
there
point
exists a
c
point
x,
C x,
there exists a
there
point
exists a
in
point
between the
in between
interval
the interval
such that the
such that
value
the
is also
value is
c.
also C.
See, this
See,
statement
this
seems to be
statement
very
seems to be
true.
very true.
This seems to be
This
very
seems to be
logical.
very logical.
There is nothing
There is
much
nothing much
to
to
understand in this.
understand in this.
If
If
the
the
function
function is
is
continuous
uh,
uh,
in a given
in a
range
given range,
and that function
and that
is
function is
constant in that
constant in
given
that
range,
given range, for example, this green curve,
then I might
then I might have always
exist
exist
a
a
point
point right
which
over
also
here which
satisfies
also
this,
satisfies this,
right?
right?
For example,
For
x equal to
example, x
c,
equal to C. at which the
f of
x
c,
f of c,
sorry,
sorry,
for which,
for which,
sorry, the f of
sorry, the f
x,
of x,
I always have
I
this
always have
x
this
such
x
that
such that the f of x is always c.
this seems to be
This
very
seems to be
trivial,
very trivial, nothing to write down.
but the reason
But the
I
reason I
took this
took this
example
example is
is I
because
want
I
to
want
tell
to
you
tell you
how do we
how do
use
we use
intermediate value
intermediate value
theorem to
theorem to
predict this
predict
answer.
this answer.
That there
That
always
there
exists
always exists
x
x
in between this
in between
interval
this
for
interval
which
for which
we have
we
this
have this
particular
particular
value as
value as
c,
c,
that
that
constant value
constant
which was
value which
there
was there
in the
in
original
the
function.
original function.
And the way the
And the
proof
way the
goes,
proof goes,
because I want to
because I want to
motivate you
motivate you how to do this proof,
because you might be
because you
able to
might
have
be
to
able to
write
have to
this
write
in
down
your
this
answer
in
sheet.
your answer sheet.
So over
So
here we
over
try
here
to
we try to
construct
construct
this problem
this problem
as a root
as a
function,
root function,
as a root
as
value.
a root value, because
Because
earlier what
earlier
I've
over
seen
here,
that over here,
this
you
theorem
know, this
sounds
theorem
like
sounds like,
we are
you know,
only
we are
interested
only
in
interested in
this
this
situation.
situation.
For
For
example,
example,
f
f
of
of
x
x
equal
equal
to
to
0,
0,
right?
right?
This
This
definition seems to
definition
be
seems to be
we
that
only
we
interested
only
in
interested in the roots of the function.
but I'm
But
claiming
I'm
you
claiming you
this
that this
function
function
is
is
not
just
limited to
not
this
limited to
situation.
this situation.
You can
You can
redefine your function.
redefine your function.
You can
You can
redefine and play it
redefine and
again
play
such
it
that you
again
can also
such that you
talk
can
about
also
this
talk
situation.
about this situation.
That's why I chose this
That's why I
example.
chose this example, that this definition is just not
Restricted to the
restricted to
roots
the
of the
roots of the
function.
function.
You can
You
even
can even
try to figure
try
out
to
the
figure out the values of x for
so that
which
you
you get
get
your
your desired
desired
output.
output.
Okay.
Okay,
So the way we
so
do
the way we do
manipulation is by
manipulation is
taking
by
a
taking a
difference
difference
and we just
and
want
we
to
just
see
want
the
to see the
difference.
difference.
We want to
We want to
calculate
calculate
at
at
which
what
point
which point
this difference
this
becomes
difference
zero.
becomes zero.
So by
So by
this
doing this
simple
simple
manipulation,
adjustment,
this
by doing this
simple
simple
manipulation,
manipulation,
this whole
you know, this
function,
whole
the whole
function, the
business of
whole business
finding
of
the
finding the
x,
x,
this get
this get
convert
convert
into the
into
business
the
of
business
finding
of
the
finding the
root
root
of
of
this
this
g
g
function,
function,
right?
right?
So what do I
So
see?
what do I see?
This
That
g
this
function
g function
has a
has a
negative value
negative value
for a given
for a
a,
given a,
right?
right?
But
But
for the given
for the
b,
given b,
this function
this
has a
function has a
positive value.
positive value.
That means there
That means
exists
there exists, just by using my
the idea of
the idea of
inverse
inverse
intermediate value
intermediate
theorem.
value theorem.
I can just
I can
claim
just
that there
claim that there
exists a
exists
root
a root, right,
for which this
for which
function
this
has
function
zero
has zero
value, right?
value, right?
And if
And
this
if
g of
this
x is
g of
zero,
x is zero for a given input,
that means there
that means
exists a
there
given
exists a
input
given
for
input
which
for
this
which this
difference is zero.
difference is zero, and that turns out to be yes,
There
this
exists a
there
value
exists a value
for
for
which
which
this
this
function
function
gives
gives
you
you
c.
c.
So this is
So
how
this is
we
how we,
you know
you know,
convert my
convert
problem
my problem
into
into
a
a
finding
finding
of
of
problem. Originally, this problem was nothing to do with the intermediate value theorem, but you can see the adjustment, the power of adjustment. So this is what we call converting your problem from one definition to the another definition.
definition to the another
And
definition.
why do you want to do that?
And
Because
why do you want to do that? Because
converting this
converting
problem from one
this
to two,
problem from one to two,
since you know that
since you know that,
since you know how to
since you
deal
know how
with
to
this,
deal with this, right?
so I just want
So
to
I just
exploit
want to
this,
exploit this, right? That's it.
because I'm very much
Because I'm very much
comfortable
comfortable, talking
talking
in
in this
terms of this
language.
language.
So I
So
converted
I
my
converted
problem
my
into that.
problem into that.
Hopefully everybody
Hopefully, everybody
get this idea,
get this idea, right? Any thumbs up
so that we can
so
move
that we
forward.
can move forward.
Okay.
Okay.
Okay, my audio is
Okay, my
breaking.
audio is breaking, right?
Oh, that's an issue
Oh,
then.
that's an issue with it
I need to
then.
figure out
Okay, I
something.
need to figure out something.
Is it still
Is it still breaking?
is still my audio is
Is still
breaking?
my audio is breaking?
I guess
I
actually
guess
basically
actually I'm
traveling a little
basically
bit,
traveling a
so
little
that's
bit,
why
so that's why I
I
have
have
a bad audio. Okay.
that's nice.
Okay.
That's nice.
That's nice. That's nice.
Okay, let's move forward.
Okay, let's move forward.
Now just
Now
want to
just want
give you
to
another
give you
important
another
result.
important
Okay,
result.
that's good.
Okay, that's good.
Audio
My
is clear.
audio is clear. Okay.
So the another
So
important
the
result
another
is
important
that
result is that
uh
uh
okay.
okay.
Can you see the
Can
screen?
you see the screen over here?
Okay.
Okay.
Okay, so my
Okay,
screen is
so my
getting
screen
shared.
is getting shared. Okay.
So in this
So in
case,
this
we
case,
want to
we want
understand.
to understand.
For example,
For
this
example,
function,
this
there
function, there
exists
exists
a function
a
which
function
is this
which is this of
function
square
which does
function
the
which does
business
the
of
business of
giving you
giving
an
you
output as
an
a
output
square.
as a square.
And we using this
And
function
using
we
this
just want
function
to
we just want to
understand
understand
that there
that there
exists a
exists
number
a number
n
n
in a
in a
positive real value
positive
which
real
has
value
a
which
square
has a
root.
square root. Okay.
uh,
Uh,
so the idea
so
is
the
that
idea is that over here,
for all
for
values
all values
which has the
which
square root,
has the square root,
we can say there
we
exists
can
a
say
real
there
number
exists a
such
real
that
number such that
if we square that
if you
real
square
number,
that real number,
we will get
we will get
n value.
that n value.
So
So
if you are getting
if you are
confused
getting
what I'm
confused,
trying to
what I'm
say,
trying to say
that
here, that
basically what
what
I'm
I'm
trying
trying
to
to
say
say
here
here
is
is
that
that
let's say I have
let's
a
say
number
I have a
n,
number n,
for example
for
number
example
5,
number 5,
okay,
okay,
and if I
and if
calculate
I
the square
calculate
of
the
this,
square of this,
and how can I
and
do
how
that?
can I do that?
I can do that
I can do
using
that
this n
using
square
this n
function,
square
right?
function, right?
Which will give
Which
me
will give me
as 25.
as 25.
So I'm basically
So I'm
trying to
basically
ask the
trying to
reverse
ask the
question.
reverse question.
Reverse.
Reverse.
Let's say
Let's
I
say
gave you
I
this
gave you this
25,
25,
right? I gave you
right?
this
I gave you
25,
this 25,
which
which
belongs to R
belongs to
plus.
R plus.
Okay.
Okay.
I'm trying to
I'm
find
trying
whether
to
this
find
thing
whether this
exists
thing
or not.
exists or not.
A reverse
A
question.
reverse question.
Why am I
Why
interested
am I
in this?
interested in this?
Why am I
Why
interested
am
in
I
this?
interested in this? Because
You know,
you might
having
be
a
having a
situation in
situation
which
in which
one way
one
the
way the
definition is
definition is
right,
true, but the other way the definition is not true,
right?
right?
Like for
Like
example,
for example, I can give you one example.
all rational
All
numbers are
rational
real
numbers are
number,
real number,
but all real
but
numbers
all
are
real
not
numbers are
rational
not
number.
rational number, right?
So you can
So
see
you
this
can see
particular
this
statement is
particular
a one-way
statement is a
statement.
one-way statement.
It's not a two-way
They're not a
statement.
two-way statement.
But
But
using this
using this
corollary,
corollary
or maybe this
or maybe
result,
this result
basically tells you
basically
that
tells you that
this statement
this
is
statement
in
is
both way.
in both way.
Okay.
Okay.
So for
So
all
for
numbers
all numbers
and the
and the
positive
positive
R plus,
R plus,
and here I have
and here I have
for a reason I
for
have
a reason I have
chosen this small
chosen
n
this small n
because this
because
small
this
n
small n
has to do with
has to do with
that
that
they
they
has
has
a
a
square
square
root.
root.
For example,
For
this
example,
25
this
is a small
25
n.
is small n.
For all such
For all
numbers,
such numbers,
there exists
there
a square
exists a
root.
square root, a proper.
I
I
mean
mean
to
to
say
say
a
a
square root.
perfect square root.
Okay, the square root
Yeah, the
means
square root means I mean to say a perfect square root. To say.
so I'm here
So I'm here
basically
basically trying to prove
the
that
inverse
inverse
statement
statement which I have
tried to
tried
explain
to
over here.
explain over here.
By just
By
converting
just
the whole
converting the whole
problem
problem
into
into
a problem
a
of
problem of
finding
finding
zeros
zeros
of
of
the
the
function.
function.
Okay.
Okay.
So we'll move
So
forward
we'll
and
move
just try to
forward
understand
and
the
just try
other
to understand the
situation.
other situation.
This is one
This
simple
is one
example
simple
which has been
example which has
discussed
been
in the
discussed in
class.
the class.
So
So
I
I
took this
took
discussion over
this
here
discussion over here because just to
to motivate
motivate
there
that
are certain
there are
situations in
certain
which you have
situations
a
in which
two-way
you have a
problem
two-way
and you
problems
just want to
and you
prove the
just want to
statement in
prove the
both way.
statement in a both way.
So once you
So
have
once
this
you have
particular
this
statement
particular
which is
statement
true
which
in
is
both
true in
sense,
both sense,
they are much more
they are much
important
more important
statements in
statements in
mathematics
mathematics,
in
in
which
which
both way they are
both
true.
way they are true.
Now we'll go to
Now
the
we'll go
second
to the second
situation.
situation.
In the second
In the
situation,
second
what do we
situation,
see
what do we
that
see
we
that
have
we
two
have two
functions.
functions.
Let's say f
Let's
of
say f of
x
x
and let's say
and let's say
g of
g
x,
of x,
and
and
such that there exists two
there exists
function
two function
such
such
that
that
for x
for
equal to
x
a,
equal to a,
f function
f
is
function
smaller
is
than g,
small than g,
but for the
but for
x
the
equal to
x
b,
equal to
the f
b, the
function
f
is greater
function is
than b.
greater than b.
And I have
And I have
shown that
shown
in a
that
graph
in a graph
over
over
here,
here,
and you can see
and you
very
can see
clearly.
very carefully,
You can see
you can
very
see
clearly
very
that
clearly that
the x
the
line,
x line,
the red line
the red
which I
line
have drawn
which I
here,
have drawn here,
the red
the
line
red line
is a g of
is a
x
g of
function.
x function.
Here I have
Here I
drawn
have drawn
using a purple
using a
line
purple line
f of x
f of
function.
x function.
So
So
you can see I have
you can
drawn
see I
both
have
the
drawn both the
functions,
functions over here.
and the
And the
assumption is that
assumption is that
it's very
it's
important.
very
You cannot
important.
just
You
forget
cannot
this
just forget this
assumption
assumption
that
that
let me write down
let me write down over here.
continuous.
Continuous.
They need to be
They need to be
continuous.
continuous.
If f of
If
g
f of g,
f of x
if f of
function
x
is not
function and g of x
continuous,
function is not continuous,
then this
then this
particular kind of
particular
thing which
kind
we
of
are going
thing
to
which we're
discuss
going to
now
discuss now
do not
do
exist.
not exist. Okay,
So
so
discontinuity
discontinuity
can
can
help
help
you
you
to
to
slip
slip away
away
this
critical
critical
behavior
behavior what you see over here.
so
So
discontinuity can be
discontinuity can be
a way out
a way out,
to
to
avoid
avoid
this
this
critical
particular
point.
critical point. But
We are
we
assuming
are
that
assuming that
f
with f
function and
function
g
and g
function
function
are
are continuous,
and we have this
and
kind
we
of a
have this kind of a
situation in which
situation in
one
which
function was
one
greater
function
than
was
the
greater
other,
than the other.
like so you can see
Like
from
you can
here
see
this
from
function
here,
is
this
greater than
function is
this,
greater than this, right?
but the moment you
But
go
the
to the
moment you
other
go to the other
extreme,
extreme,
the situation is
the situation
otherwise.
is otherwise.
So what do we
So
see
what do
that
we see
we
that?
see that
We see that
there exists a
there
function
exists
h
a
of
function h
x,
of x,
which also
which also
passes
passes
through that
through that
particular
particular intersection point at which
f of x
f of
and f
x
of
and f
g
of g
has crossed.
has crossed, right? Because
If I assume
if
that
I assume that f of x and f of g
is
of
a
x
continuous
is
function
continuous function,
and they had
and
this
they had
situation,
this situation,
then
then
definitely
definitely they might have met somewhere, right, in between.
then definitely
Then
this
definitely
function
this
might
function
have
might
cut each
have
other,
cut each other,
and they are very
and they
important
are very
because
important because
if I see this
if I see
situation
this situation,
which I have talked
which I have
earlier
talked earlier,
over here,
over here,
over here,
over
what I
here,
see,
what I see that,
what I claim
what I
that
claim that
we don't have
we
any
don't have
roots.
any roots.
We do with
We
there
do with there exists no such x value
for which
for
both
which both
are
are
satisfied
satisfied
together,
together.
and you can
And you
see
can see
using this
using
argument,
this argument,
you can see
you can
that
see
using this
that using
argument
this arguments what I have discussed here,
that
that
this equation
this
don't have
equation
any
don't have
roots
any roots
because
because
you have two
you have two
functions
functions
over here,
over here, f
x and
of
g of
x and
x,
g of
they
x.
don't
They
satisfy
don't
this,
satisfy this,
right? So
right?
they don't have
So
any
they don't have
situation
any
to get cut,
situation to get cut, right?
because one
Because
function
one
was
function
always
was
above
always
than the other
above
function.
than the other
If
function.
you see very
If you see very
carefully,
carefully over here,
your
your
e
e
of
of
minus x
minus x function
was
was
always
always
greater than the
greater than the
minus x,
minus x,
always greater than
always
this.
greater than this.
So whenever you
So
have
whenever
this
you have this
hierarchy
hierarchy, when one function is
always has a
always
greater
has a
value than
greater
the other,
value than the other,
then
then you
you might
might
expect
expect
there
there
is
is
no
no
intersection,
intersection, right?
because this is true
Because
for
this is
all
true
values
for
of
all
x.
values of x. That's why I said
The roots
the
don't
roots
exist.
don't exist.
But in this
But
case,
in this case,
this important feature, and this important feature, along with this given assumption, guarantee it gives you guarantee that f function and g function intersect at x equal to c. That's important, right? And the next idea I'm going to discuss now is that there
is that
exists
there exists
h of x,
h of
which
x,
also
which also
passes
passes
through that
through
particular
that particular
intersection point.
intersection
And
point.
the way you can
And the way you
construct
can
that h of
construct that
x
h of
is
x
just by
is
taking
just by
the
taking
difference
the
of the two
difference of
original
the two
function,
original function,
right?
right?
And here we
And
have
here
this
we have this
particular
particular
small
proof, a
proof
small proof,
that why this
that why
function,
this
the new
function, the new
constructed
constructed
function, which is the
function, which is the
difference of the
difference
two
of the two
function,
function,
passes through the
passes
same
to the same
intersection point,
intersection point,
right? So you
right?
might
So
have
you might
this
have this
as an
as
MCQ
an
question.
MCQ question.
We have two
We have two
functions
functions f
f
and
and g,
g, they are
they are continuous
continuous such that
they
they
satisfy
satisfy
this
this
condition.
condition.
So they might
So they might
there might be
so there
one
might be one multiple
choice
choice
statement
statement
that
that we
there
have
exists
there
a
exists a
function
function
which also
which
passes
also
through that
passes through that
intersection point.
intersection point.
Then you might have
Then you
another
might have
statement,
another statement,
there exists an
there exists an
intersection point.
intersection
So they
point.
can
So they
create
can
such
create such an
innovative
innovative
questions
questions
in exams.
in exams.
Okay.
Okay.
So I
So I
basically
basically projected this set of discussion
in the terms
in
of
the terms of
exams.
exams.
I mean to say. Now let's go to the another important idea, which we call as the fixed point theorem, where we have a function which is defined in an interval and
There
gets
we
mapped
have
into another
a
interval,
function which is defined in an interval
and the assumption is that the
and gets
function is
mapped into another
continuous.
interval. And the assumption is that the function is continuous.
I guess my screen got stuck, right?
I guess my
It's
screen
frozen.
got stuck, right?
It's not
It's got
moving at
frozen.
all.
It's not moving at all.
Okay, that's
Okay,
it's working.
that's working now.
I think so. I have a
I
very
think so. I have
bad
a very
internet.
bad internet currently.
Okay, I'll fix
Okay, I'll
this.
fix this.
So now you want to
So now
discuss
you want
this
to discuss
fixed
this
point
fixed
theorem.
point theorem.
So this fixed
So
point
this
theorem,
fixed
you can
point theorem,
see
you can see
that I
that
have a
I have
function
a function
that is defined in
that
an
is defined
interval
in an interval
and get mapped
and
to
gets
another
mapped to
interval,
another interval.
and
And the assumption is that we have a continuous function.
and I have
And
drawn
I
a
have drawn a
plot
plot here
to
to
illustrate the idea.
illustrate the idea.
To
To
illustrate the idea,
illustrate the idea,
and we will
and we will
just bring
just
the same
bring
set
the
of
same set
arguments
of arguments
which we have
which we have
discussed
discussed
above.
above.
Same set of
Same set
arguments
of arguments
will also
will
hold
also
here
hold here
in order to
in
discuss
order to
this
discuss
theorem,
this
because this
theorem,
above
because this
discussion
above discussion
leads to a
leads
theorem.
to a theorem.
This is this.
This is this.
Theorem
The
tells you
theorem
that
tells you that
there
there
exists
exists
there
there
exists a
exists a
value
value
in this
in
value.
this value.
You can see
You
over
can
here
see over here
whether
whether
in this value
this
in which
value
we can
in
say
which we
that
can
there
say that there
exists
exists
an
an
intersection,
intersection,
right?
right?
In here we are
In here we are
basically
basically
taking
taking two functions.
this
This
black function
black
which you see
function which you
here,
see here,
and here we
and
have
here
this
we
another
have this
function
another
which is
function which
just
is
g of
just
x,
g of x equal to x,
which is shown in
which
the
is
red
shown in
color,
the red color, and this is shown in the black color, f of x function. This f of x function can be any general function, but the idea is that the second function which we have taken here is a constant function. This a linear function, which is g of x equal to x. And the idea why we are saying this is a fixed point, because the definition of the fixed point is this, in which in which the input is same as output. This is the definition of fixed point. So this theorem basically tells you that whether do we have this particular situation or not, you can investigate in that given function. You can investigate. There exists at least one fixed point if you have these situations, right? Where the one function is more than the other, and in the other values for the other, for here you can see the function fx is more than the second value. Like over here you can see therefore 0 is greater than the g of 0. But in the other extreme, you have completely opposite behavior in which the function is less than the g of x. So you are guaranteed, because of the above set of discussion and argument, there exists an intersection point. So if there exists an intersection point, at least one intersection point, then we see that there exists a fixed point, because the definition of the fixed point is the value which you get is same as the input which you give to the function. I hope this all this set of ideas are clear to you. Any questions so far? You can write down in the text box. I don't have any question, or yes, no, something, anything you feel. Should I can move forward, right? I can go now to the extreme value theorem. Any question so far? You can write down in the text box. It's fine. Okay, now we will move to extreme value theorem. So this extreme value theorem is important because it tells you about the extremum values of the function. So before to start this extremum value theorem, first I want to tell you about various situations. Such that what do we mean by bounded set? What do we mean by closed? What do we mean by open? What do you mean by interior? If all these ideas and words, all these jargons are clear to you, there are various definitions, there are various theorems. To understand those theorems will become very easy to you. So the way we can start now our discussion is that, let assume we have a continuous function in a given range, sorry, in a given domain. So here the domain is an interval, and this interval gets mapped to a real line in this given function f, and we say that the function is bounded on this interval, and the function is bounded in this interval, and this is guaranteed by this extremum value theorem. So that's the idea behind the extremum value theorem. Okay. So more to discuss more explicitly what this extremum value theorem, first I want to clear some of the definitions to you. Like for example, the word which I've used here, something called as a bounded. So what do you mean by bounded? What's the idea of something called as a bounded, or something called to be a bounded? So I have written down here some examples of the bounded set. The first thing which you see that I have written down in the red color, the bounded set, which basically tells you that there exists a set. This definition basically tells you that I have taken a subset of real number, right? For example, see, real number is also a set, right? A set of numbers. You can always create a subset out of a real number, right? And let's say I have created a random subset, some random subset. I don't know what numbers I have to choose. I just pick the random numbers, okay, just out of this real line, and I call that particular set as S set. And I claim that this S set is a bounded set. So why do I am saying that this is a bounded set? For that we need to understand. So here I have written the condition, the logic, the idea, that why am I saying that S set, which is a subset of a real number, is bounded. So the idea is that The reason behind that I'm calling it as a subset because there exists
m
m
greater than
greater
real
than
number.
real number.
That means there
That means
exists
there exists a very large value in a real
such
number
that,
such that,
okay,
okay,
there
and
exists
there exists a very small value
in a real
in a
number,
real
small
number,
value.
small value.
This might
This
be
might be
having a
having
large
a large
magnitude. That's
magnitude.
another
That's
story.
another story.
And the reason
And
why
the
it is
reason why it
small
is
number,
small in the sense of negative as well.
like for
Like
example,
for example,
minus
minus 1000 is smaller compared to minus 100, right?
and you
And
understand
you
why
understand why am I
saying that
saying
minus
that minus
1000 is
1000 is smaller compared to
minus
minus
100.
100?
So that's
So
the
that's the
idea
idea
behind
behind over
that I
here,
have
that
a
I have
large
some
value which can
value
be
which can
large
be
negative.
large negative.
So I do
So
always
I do always
exist
exist two
capital
numbers,
M and
capital M
small
and
m,
small m,
such that
such that
all the
all
values
the
in this
values
set
in this set
lies inside
lies
this
inside
interval
this interval,
which is
which
created
is
using this
created
small
using
m
this
and
small m
capital
and
M.
capital M.
I can always
I can
create an
always create
interval
an interval, right, using this
small m and
small
capital
m
M.
and capital M, right?
So this
So this
interval
interval which I have made using this two, because in order to have an interval,
I just need
I
two
just need
points
2 point, right?
and I call
And
that
I
as
call
my
that 2 point as in my boundary point of that interval.
I will
I
create
will
an
create an
interval.
interval.
So basically
So
this whole
basically, this
statement
whole
tells you
statement
that
tells you that
there
there
exists an
exists
interval
an interval
for
for
which
which
all the
all the
values of
values
this
of this
set
set
S
S
lies
lies
inside
inside
that
that
interval.
interval.
All here I can see I have written as all values of x of the set S satisfies this particular situation. So if I found that, then I say that this S is a bounded set. I hope everybody get this idea. I just need one thumbs up that you got the idea of bounded set, because over here now it seems to be very obvious, but I don't want you
I
to
don't
guys
want you to
forget
guys
this
forget
definition,
this definition in exam,
because again this
because
might be
again
one
this
of
might
your
be one of your
MCQ
MCQ
in
in
which
which
they will change
they
some
will
notation.
change some notation. For example,
Instead of there
instead
exist,
of
they
there
might write,
exist, they might write for all.
let's say over
Let's
here
say
they will
over
write
here
there
they will
exist,
write there exist,
and
and
we
we
know
know
that
that
these
these
two
two
are
are
situations
different
altogether.
situations altogether.
We don't want to
So
mess
we
up
don't
this
want to mess up this
basically. We
basically.
just don't want to
We just
mess up,
don't want to mess up,
and I hope
and I
everything
hope
will be fine.
everything will be okay.
So there is another
So there is
definition
another
over here.
alternative definition.
If you're not
If
getting
you're not
what
getting
is what I've written
what I
here,
have
I can
written
show
here, I
you
can show you
in a graph.
in a graph.
Let's say
Let's say
no.
no.
Let me use
Let
one
me use
dimensional graph.
one dimensional graph because we are doing things in one dimensional, right?
So this is your
So
real
this is
number,
a real number, right?
and let's say
And
I
let's say I
chose
chose
this
this
numbers as a
numbers as
randomly.
a randomly, right?
So
So real numbers might belongs to the S set, right?
which is a
Which
subset
is
of
a
real
subset
numbers.
of real numbers.
I hope
I
everything
hope
is
everything
visible.
is
Screen
visible,
is
right?
visible,
Screen
right?
is visible, right, to you?
So all the
So all
markings
the
red colors
markings,
are
red
visible.
colors are visible, right?
Just want to make sure,
Just want
right?
to make sure, right?
Okay.
Okay.
So the idea
So the
is
idea is
I can always
I can
create.
always create.
There always
There
exists
always
an
exists
interval.
an interval.
For example,
For
this
example, this
in this real
in
line,
this real line.
and I'll call
And
this
I'll
lower
call this
limit
lower
of this
limit of
interval
this
as small
interval
m,
as small m,
and always
and
have
always have
this upper
this
limit of
upper
this
limit of
interval
this
as
interval
capital
is
M.
capital M.
So I can
So I
always
can always
create. There
create.
always
There
exists
always exist
interval
interval
such that
such that
all these red
all these red
dots,
dots,
all this red
all
dot
this red dot
belong to that
belong to
interval.
that interval.
This interval.
This interval.
Hope now
Hope
this
now this simple definition
is
looks
easy to you.
easy to you.
Now
Now
what
what
I'm
I'm
trying
trying
to
to say that
an
an
alternative
alternative
definition to this.
definition to this.
So it's over
So
here.
it's over here. Yeah.
Over here we
Over
see an
here we see an
alternative
alternative
definition.
definition.
So instead
So
of
instead of
defining
defining
a lower limit
lower limit
and upper
and
limit
upper limit
explicitly,
explicitly,
we can
we
define an
can define an
interval
interval
using just with
using
one
just
number.
with one number.
The only
The
difference
only
between
difference
this
between
definition
this definition and this definition
is the way we
is
are
the way we are
defining an
defining an
interval
interval
around that set
around that
S.
set S.
You can see in
You
this
can see in this
alternative
alternative
definition we have
definition
this
we
S
have this
set,
S
and
set,
I call
and
that
I
as the
call that as
bounded.
the bounded.
If
If
I can always
I can
create an
always
interval,
create an interval,
k is something
k is
called as a
something called
large
as a
value,
large value, for example, let's say,
which is a
which is a
positive. This is
positive.
very
This is
important.
very important. This is a positive,
Such that
such that
I can
I can
calculate the
calculate the
distance.
distance.
I can
I
calculate
can
the
calculate the
distance
distance
of the
of the
elements of
elements
set
of
S.
set S. let's say the in S set I have an element, let's say this X.
In that
In
particular
that
set,
particular set,
I have
I have
numbers.
numbers.
All
All
the
the
values
values
in this
in
S
this
set,
S set,
if I
if I
calculate the
calculate the
distance from the
distance from the
origin,
origin,
that
that
distance
distance
will
will
always
always
less
less
than
than
that
that
k
k
value.
value.
And that's the
And
reason
that's
why
the
I've
reason why I
chosen
have
this
chosen this k to be positive number, because I know the distance is always positive, right?
So I can say
So I
that
can
the
say that
distance
the
of
distance
all
of
the
all the
values of this
values of
set
this set
S,
S,
it is
you know,
bounded,
it is bounded by some
number,
number,
right?
right?
I can
I
always
can always
have this
have
number
this. I can always find this number, positive number, such that all the distances are
inside this number.
inside this number.
So
So
I can
I can
show
show
to you
to
over
you
here.
over here.
For
For
example,
example,
like here, for example, this is my real number, like okay, and over here we have origin 0, and let's say I have points. On my screen, am I audible?
am I audible?
I don't think so.
I don't
I
think so.
guess.
I guess.
Am I clear to
Am
all?
I clear to all?
So the idea
So
over
the
here
idea
is
over
that
here is that
if I try to
if I
calculate
try
the
to
distance
calculate the
from the
distance
origin,
from the origin,
right?
right?
So this
So
distance
this
turns out
distance
to be,
turns out to be,
bounded
bounded
by some number
by
k.
some number k.
K is
K
positive, so
is
there
positive,
always
so there
exists a
always
k.
exists a k.
I mean,
I
for
mean,
example,
for
this.
example, this.
If I just
If
calculate
I
the
just
distance
calculate the
from the
distance from
origin,
the origin,
this
this
distance will be the
distance will be the
maximum.
maximum, right?
So you can say
So you can
this
say this
all those red
all those
points
red points,
which belongs
which
to
belongs to
this
this
set S,
set S,
which is a
which
subset
is
of
a
real
subset
value.
of real value.
So if I
So
calculate
if
the
I
distance
calculate
of
the
these
distance
red
of this
dots
red
with the
dots with
origin,
the origin,
those distance,
those distance,
you can say
you
I
can
can
say I
always
can always
create
create
a point
a
on
point
the
on the
real line
real
such
line
that
such that
the distance
the
of that
distance
point
of
from the
that point from
origin
the origin
is
is
maximum.
maximum, right? It's
Maximum over
maximum
all the
over all the
distances
distances what I can have from
the
the
values of the
values of
set
the
S.
set S.
So that's
So
what the
that's what the
graphical idea
graphical
behind
idea
this
behind this alternative definition as well.
Now I'll give
Now I'll
you
give you
examples. For
example.
example,
For
here we
example,
have
here we have two
short
examples: short
example and
example
this
and this
little zoomed
little
out
zoomed
example.
out example.
In this
In
example,
this
you can
example,
see
you
that
can see that
there exists a
there exists
function
a function
which is defined
which
in
is
such a
defined in
way,
such a way,
and what do we
and
see
what do we
here
see here
is that there
is that
exists
there
a
exists a
maxima,
maxima,
minima.
minima.
You can say the
You can
point
say
of
the point
maxima.
of maxima, right?
The point of
The
maxima
point of
is where
maxima
you
is
have
where you
this
have this
particular point in
particular
which you
point in
have a
which you
zero
have a
slope,
zero slope, right?
and over here
And
you
over
have a
here you
point
have
in
a
which
point
also
in
there is
which
a
also
slope.
there is a zero slope.
So
So the characteristic feature of the
maximum
maximum
minima is
minima
that
is that at
at those
those
point
point
you
you
have a
have a
zero
zero
slopes.
slopes.
If you can try
If
to
you can try
calculate
to
the
calculate the
derivative,
derivative at this point,
that
that turns
turns
out
out
to
to
be
be
zero.
zero.
So
So
that's
that's what
what
I mean by
I mean
maximum
by
minima.
maximum minima.
Okay.
Okay.
So the idea
So
over
the
here
idea
is
is that in this particular
you can
case, you
see
can see
the whole
the whole
black color,
black color,
which is the value
which
of
is
the
the value
function.
of the function, these are the
Is
functions,
bounded.
is bounded,
Which is
which is
sandwiched between
sandwiched
these two,
between these two,
capital M and
capital
small
M
m.
and
You can
small
see.
m. You can see.
This function
This function
can be
can
closed
be closed
inside this
inside this
particular
particular
two
two
horizontal
horizontal
blue lines.
blue lines,
And you can say
and
the
you can say the
values
values
is confined
is
within this
confined within this particular
values
values
over here.
over here.
And you can also
And you
see
can
a
also
similar
see a similar
situation over here.
situation over here.
And in this
And
case,
in
you
this
can
case, you
see
can see
I
I
have
have a
various
various
point of
point of
maxima, minima.
maxima,
You can
minima.
see
You
over
can
here,
see over here,
right?
right?
And all these
And
points are
all these
because
points
of
are
the
because of the
slope being
slope
zero
being
at that
zero at
particular
that
point.
particular point.
But you can
But
still
you can
see
still
that
see that
the global
the
maxima,
global
the global
maxima, the
maxima
global
is over
maxima
here
is over
somewhere.
here somewhere.
Over here,
It's over here.
global maxima
Global
is over
maxima
here.
is over here.
These are some
These are all
local
some local maximas, right?
local
These are local
maximas. These are the local
maximas. These are
minima.
the local minima.
Yeah, the
Yeah, the
locally
locally
where it becomes
where it
maximum
becomes
value
maximum
locally.
value locally, right? We can always create an interval,
If I see
and
this
inside that
interval, I
interval,
see this
I
is
see this is the
minimum value.
minimum value, right?
Even though the
Even though the
overall
overall
globally,
globally, if you check,
the minimum
the minimum value is over here.
But no matter
But
what
no
the
matter
value,
what the value
right?
is,
No matter
right?
what the
No
value
matter
of the
what the
function
value of the
takes
function takes
in this graph,
in this graph,
I can always
I can always
confine
confine
these
this whole
values
values
inside
inside
these two
these two
vertical
vertical
lines,
lines.
and I call
And
this
I call this two
extremum
vertical lines as my
extremum values,
extremum values.
bounds on
Bounds
this
on this
function,
function, bound.
and it's very
And it's
important
very
to know
important to know whether this function is bounded or not,
because this
because
might
this
have a
might have
very
a very important
important
experimental
features,
features,
implications.
implications.
You might be
You might
interested
be interested whether
whether
this
this
is
is
bounded or
bounded or
not. For
not.
example, when you're
When
trying
you're
to do
doing
some
some computation
computation on a computer
and you want to
and you want to
understand
understand whether this
whether this
computation will take
infinite amount of
infinite
time,
amount of
just
time,
10
just
amount of
10
time,
amount of time, 10
10 seconds,
seconds,
1 year,
1 year,
billion of
billion
years,
of years,
and if your
and if your
calculation takes
calculation takes
billion
1
years,
billion
then there is
years,
no
then
point
there
of
is no
doing
point of doing
calculation.
calculation, right?
So
So
that's what I'm
that's what
trying to
I'm trying
illustrate
to
here.
illustrate here.
So this is
So
what we
this is
mean by
what we mean by
bounded set.
bounded set.
And
and
since I
and since I
use the word
use
called
the
as
word called as
maxima
maxima
minima,
minima,
so that's
so
what
that's what our
further
further
point of
point of
discussion
discussion
is that
is
we
that
have
we
this
have this
idea called
idea called
something
something
called as
called
a
as
maxima,
maxima,
and we say
and we
that
say that
this given
this given
point C,
point C, any point,
I'm saying that
I'm
there is
saying
a
that there's a
point
point
maxima. I'm
maxima. I'm
calling that
calling
point
that point as
C,
a C,
which is
which is
inside this
inside this
interval,
interval,
because the
because
point of
the point of
maxima
maxima
is
is
is a label
is a
which is
label
given
which
to
is
one of
given
the
to one
value
of
of
the
the
values of
x,
the x,
like over here,
like over here,
for which the
for which
function
the function
for which the function takes
takes
the
the
maximum
maximum
value.
value, right?
So I
So
have a point,
I
I'm
have a
calling
point,
that
I'm
as a
called that as a
maxima,
maxima,
said to be
and
a
said to be a
maximum of
maximum
this function,
of this function
when
when,
if I
if I
calculate the
calculate
values
the
of
values
function
of function
at all
at
given
all
values
given
in this
values in
domain,
this domain,
that all
that
values
all
turns out
values
to
turns
be
out to be
smaller
smaller
than the value
than the value
corresponding to the
corresponding to
maximum,
the maxima,
right? So if you
right?
want
So
to
if you
see
want
that
to see that,
in a proper
in a
sense,
proper sense,
I can show
I
you
can
that
show
in
you
this
that in
sense.
this sense.
Let's say over
Let's say
here,
over here,
let's say this is
let's
x
say this
equal
is
to
x
c,
equal to c,
this is
right? And
some
this is
f of
some
x
f of
function.
x function.
So what do I
So
see
what
here?
do I see here?
Over here,
Over here,
this is what my
this is
f
what
of
my
c
f of
is,
c is,
right?
right?
And you can
And
see
you can
this is
see this is right here, f of c, right?
and you can
And
see
you can
that
see that very
you can see
carefully.
very
You can see
clearly
very clearly.
if I
If
calculate
I
all the
calculate
values
all
of
the values of
fx,
fx here,
they are
they are
always less
always
than
less than
this
this
particular vertical
particular
line
vertical line over here,
fx
fx
small
small
over
over
here,
here.
you can see,
You
right,
can see, right?
this
This
horizontal line.
horizontal line.
This horizontal
This
line
horizontal line
is
is
basically a
basically
line.
a
You can
line.
see
You
all the
can see
values
all
of
the
this
values of this
line are
line
greater
are
than
greater than this
value of the
value
function.
of the function, right?
So that's why
So
we
that's
call
why
this
we call
x
this
equal to
x
c
equal to c
as my
as my
maximum point,
maximum point,
or this is
or
the
you can
point
say
of
the point of
maxima.
maxima.
This is the point
This
of
is the point of
maxima.
maxima. Okay.
So
So
this is the way we
this is
can
a way
write
we can
down
write down
in a
in a
in an
in an
interval way,
interval way,
and
in a
basically in an
basically in
equality
an
way.
equality way.
Some people
Some
write
people write
in this
in
sense
this
as well.
sense as well.
This is the
This is the
most
most
professional way of
professional way of
writing
writing
of maxima.
of maxima.
So what do we
So
see
what do we
that
see that
we
we
basically calculate
basically
the value
calculate
of
the value of
fx
fx
over a given
over a
interval
given
here,
interval here,
right?
right?
And what I will
And
do,
what I will do,
I will just
I will
find
just
out
find out what is the
maximum
maximum
value
value
of
of
fx
fx
in
in
this
this
domain.
domain, right?
And the moment
And
I
the
found the
moment I found the
maximum one,
maximum one,
I will
I will
assign that
assign
value
that
as f
value
of
as
c.
f of c.
So this
So
basically
this
tells you
basically,
that
this notation basically tells you that
you have
you
over
have
here
over here
the
the
whole set of
whole set of
values,
values,
but just give
but
me
just
the
give me the
maximum one.
maximum one.
Just give me what is
Just
the
give me what is the
maximum.
maximum, that's it.
You calculate
You
for all
calculate
values
for
of
all
x
values of x
starting from a
starting
to
from
b,
a to b,
and you just
and
give
you
me
just give me the maximum value of
maximum
this. That's it.
value
Maximum
of
value of
this
this
fx.
fx.
So that is
So
what
that is what
this whole
this whole
notation is trying to
notation
tell
is
you.
trying to tell
It's
you.
just a way
It's
to
just a
write
way
down.
to
Just
write
give me
down.
the
Just give me the
maximum.
maximum.
Calculate
Calculate
for
for
all
all
values
values
of
of
x
x
in
in
this
this
interval
interval
and give me the
and give me the value of x,
maximum value of
maximum
x.
value of fx.
And the exact
And the
same
exact
definition
same
holds
definition
true for
holds
the
true for the
point
point
of
of
minima as well.
minima
Let's
as
say
well. Let's say
I
I
have
have
a
a
point
point
of
of minima,
c.
let's say d.
So we can
So we
say
can
that,
say that very comfortably,
for
like
example,
for
this.
example this.
So I can
So I
see
can see
that this
that
is
this is
f of
f
d,
of d,
and this is the
and
point
this is the
of
point of
minima,
minima,
and you can see
and you
all
can
my
see all
values
my
of
values of
fx.
fx,
All my
all
values
my
of
values of
fx is
fx is
greater
greater
than the f of
than
d.
the f of d, right?
This is your f
This
of
is
d.
your f of d. D, which is horizontal line.
This is your f
This
of
is
d,
your f of D.
and all the
And
values
all
of
the
f
values of
is
f of
greater
D
than
is
the
greater than the f of
f of x
f of x function is greater than the f of d. This is what written over here.
and this is how
And
I
this is
figure
how I
out
figure out
this
that
point
this
is my
point is my
point of minimum.
point of minima.
Okay,
Okay,
and
and
this again
this again
definition
definition
basically tells you
basically
that
tells you
you
that
just
you
calculate
just
the value
calculate
of
the value of
function
function,
start from a
start
to
from a
b.
to b.
So whatever
So
the
whatever
value
the
is
value is
minimum,
minimum,
paste it
just
over
paste
here.
it over here.
That's it.
That's it.
So
So
that's the
that's the
definition of
definition of
maximum minimum,
maximum minima.
and we will
And we will
move on
move
to
on
the
to the
next
next
definition,
definition,
which
which
is
is
called
called
as
as
results of
results
this
of this
definition what we have
definition
wrote
what we
here.
have wrote here.
So the idea is
So the
that
idea is that
so when
so when
the function
the
is
function is
bounded,
bounded,
so whenever
so
say
whenever
function is
say the
bounded,
function is
that means
bounded, that
function
means
is bounded
function is
in
bounded
above
in above sense as well as in the lower sense.
okay.
Okay.
So you can
So
see
you
that
can see
this
that
maxima
this
can
maxima
act
can act as an upper bound to the function
independently,
independently, right?
and this
And
function can
this
whole thing can
whole
be
thing can be
act
act
as a
as a lower bound for the given function.
but when I
But
say
when
the
I say
word
the word
bounded,
bounded,
so it is
so it
bounded
is
in the
bounded in the
above and the
above and
below
the
sense
below
both.
sense both.
If the
If
function
the
turns
function
out to
turns
be
out to be,
bounded from
bounded from
above
above,
but not
but
bounded
not
from
bounded
below,
from below,
we don't call
we
that
don't call
function to
that
be
function to
bounded.
be bounded.
We just say
We
that
just
the
say
function
that the
is
function is
bounded above.
bounded above.
That's the proper
That's
way
the
of
proper
writing
way
down
of
things.
writing down things, right?
So
So if you haven't got the
understand
idea what do I
like what I'm trying
like
to
what I'm
say
trying
here,
to say here, I can write down over here.
let's say I have
Let's
a
say I have a
situation
situation.
this.
This
Okay, this is your
this
function
is your
e to the
function
power
e to the
minus
power minus
plus
sorry
x.
plus x.
We can see
We
that
can see
this
this
function
function
is
is
bounded from
bounded
below,
from below,
right?
right?
Because if you see
Because if
very
you see very
carefully,
carefully,
this function
this
is
functions
asymptotically starts
asymptotically
with
starts with
0, right?
0, right?
Asymptotically starts with
Asymptotically
0,
starts with 0,
and this
and
goes
this
to
goes to
infinity, right?
infinity, right? As x goes to infinity.
But the moment
But
I
the
take
moment I take
the f of
the f
x,
of x,
but x
but
tends to
x tends
minus
to minus
infinity,
infinity,
this goes to
this
0.
goes to 0.
So what do we
So
see
what do
that?
we see that?
We see
We
that
see that this function f of x,
where the domain
where the
is
domain is
the
the
complete real
complete
line,
real line,
but get
but get
maps
maps to
0
0
to
to
infinity.
infinity, right?
And see
And
very
see
carefully,
very carefully, I have
taken here
taken
as an
here as a
open interval,
open
not a
interval,
closed
not a
interval.
closed interval.
See over here,
See over here, very
I
carefully. I
have
have
selected an
selected
open
an
interval,
open
not a
interval,
closed
not a
interval.
closed interval.
This is
This
different.
is different.
See, this is
See, this is
different,
different,
this is
and this is
different.
different.
This means
This means
included, this
included.
means
This means
excluded.
excluded.
Okay,
Okay.
so
So
here I have
here I
taken
have taken basically I have basically
how
wrote
my real
how my
line is
real line
getting
is
mapped
getting mapped
to an
to
open
an
set.
open set.
This is an
This
open
is
set
an open set
because 0 is
because
not
0 is not
included in
included
this
in
set,
this set,
and
and
infinity
infinity
we never
we can
include.
never include, right?
So
So
infinities are always
infinities are
open,
always open.
they're never
They're
closed.
never closed.
There is another
There
way
is
you can
another way
write
you
down
can write
this.
down this.
So left hand
So
part
left
would
hand
be the
part would be
same,
the
but
same,
we can
but
write
we
down
can
this
write
whole
down
thing
this whole thing
as my R
as my
plus.
r plus. Okay,
Because
because
my R
my
plus
r
is
plus is
basically the
basically the
positive part of
positive
the real
part of the
number,
real number, right?
and that is
And that is
actually
actually
you know 0
0
excluded.
excluded,
It starts from 0
starts
and
from
goes
0
to
and goes to
infinity.
infinity.
When someone
When
talks
someone
about
talks about what is the real negative,
it's
it's
basically
basically
this, right?
this, right?
Starts
It
from
starts from
negative
negative
infinity
infinity
and
and
ends till
ends
0.
still 0.
Both are not
Both are
included.
not included, right?
And if someone
And if
tells you
someone
what is
tells you what is
you know
you know
just 0,
just 0, right?
so you can say
So
in
you can
both the
say in both
cases
the
0
cases
is
0
not
is not
included
included
because
because
neither
0 is
positive
neither
nor
positive nor
negative.
negative, right?
So we need to be
So you
very
need to be very
careful.
careful about that idea.
And what we
And
see
what we
here
see here in this example,
that this
that
is
this is bound
bounded
lower,
this is bounded
this is bounded
below.
below.
Okay, this is
Okay,
bounded
this is
below
bounded below,
but not
but
above.
not above.
We can have
I
another
can have another
situation
situation
which
in
the
which
function
the
is
function is
bounded
bounded
above but not
above but
bounded
not
below.
bounded below.
Let me draw
Let
that
me
particular
draw that
graph.
particular graph.
For
For
example,
example, like this.
um,
Um,
let's say I have
let's say I
function
have function
which is
which
defined
is
from 0,
defined from 0,
and see
and
very
see
carefully
very
here
carefully. I have taken as a 0 as an open interval because
because
this
this goes
goes
to
to
infinity.
infinity, right?
So
So
function is not
function is
defined,
not
and we
defined, and we
cannot
cannot
remove
remove
this
this
this particular
this
problem.
particular problem.
And
and it goes to this,
and the values
and the
which
values which can take
goes from
goes from
0 to
0 to,
oh sorry
oh sorry,
minus
minus
infinity
infinity
to 0.
to 0.
And in this
And
function
in
you
this
can see
function you
very
can see
clearly
very clearly
that over
that
here
over here
this is not
this is
bounded
not
below,
bounded below, right?
but this is
But this
bounded
is bounded
above.
above.
This is bounded
This is
above,
bounded above,
and in this
and
case
in
it is
this case
bounded
it is
below.
bounded below.
And
Right?
the
And the
how they are
how they
bounded
are bounded
above, you can
above,
see
you can
here
see here
this is your
this is your
asymptote value
asymptote value
which
which
goes
goes
to
to
0, right?
0, right?
I mean,
I mean,
x-axis
x
goes to
axis
this,
go to
but
this,
your
but
y
your
axis
y
goes to
axis
0.
goes to 0.
As your x
As
goes
your
to
x goes to
infinity,
infinity,
let me write it
let me
more
write it more
properly
properly
so that we
so
don't
that
have
we
any
don't have any
confusion.
confusion here.
The
You
f
know,
of
the f of
x
x
goes to
goes
0
to 0
when x
when
goes to
x goes to
infinity.
infinity.
So that's the
So
idea
that's
over
the
here,
idea over here,
right?
right?
So you might have a
So you might have a
situation
situation in which the function is bounded
above
above
but not
but
below,
not below,
and vice
and
versa.
vice versa.
So
So
we say
we
that the
say that the
function
function
is
is
bounded.
bounded.
That means when
That means when
function is
function is
bounded
bounded
below
below
plus
plus
above,
above, both
both should be
both should
included.
be included.
If any one
If
is
any
not
one of is
included,
not included,
then we don't say
then
the
we don't
function
say
is
the
bounded.
function is bounded. Okay.
And if
And
even if
if
this is true,
this is true,
and if the
and
function
if
is
the function
bounded,
is bounded,
it
it
is
is
true, we
true,
can write
we can write down
that as an
that as an
interval
interval
definition that there
definition that there
exists a
exists
capital
a
M
capital M
greater than
greater
0
than 0
such that
such that
f of
f
x,
of x,
the mod of
the
f of
mod of
x
f of x,
is greater
is
than
greater
M
than M
for all
for all
x
x
belong to the
belong
domain
to
of
the
f.
domain of f.
I hope
I hope
this
this
definition is
definition
clear
is
to all.
clear to all.
So this is an
So this is
interval
an
method to
interval
write
method to
down
write down
what do we mean
what do we
by
mean by
definition. So
definition.
what do we mean
So
by
what do we mean
bounded
by
function?
bounded function?
So let me
So
write
let
down
me
this
write
as
down
a
this as a,
you know
you know,
interval
interval
definition
definition
for bounded
for
function.
bounded functions.
Okay.
Okay.
So the
So
idea is that
the
very
idea is that
simple
very simple, right?
because
Because
if you are not
if
able
you
to
are not
capture
able to
this,
capture this,
I can tell you
I can tell
how
you
we
how
are
we are
able
able
to
to
see this
see
particular
this particular
statement.
statement.
And we can see
And
this
we can see
particular
this particular
statement
statement
is that let's say
is
the
that, let's say
function
the
is
function is
bounded
bounded,
like
like
some
some,
like this for
like this, for
example,
example,
right?
right?
So I can
So I
always
can
create
always create
uh,
uh,
I can always
I can
create
always
these two
create this
vertical
two
line
vertical line,
which
which
is m
is M,
and over here
and
it
over
is
here it is
minus m,
minus M,
right?
right?
And
And
inside these
inside
two
this two
horizontal
inside
line
this two horizontal line,
my whole
my
function
whole
can
function
get
can be get
contained.
contained.
So you can see
You can
basically
see
what I'm
basically
trying to
what
do
I'm
here.
trying to do here.
Here I'm
Here
basically
I'm
trying
basically
to
trying to
find the
find
distance
the
of my
distance of
function,
function,
the value of
the
the
value of
function
the
from
function
the
from the
origin.
origin.
Here you can see
Here
this
you
is
can see this
origin.
is origin,
So
right?
what I'll
So
do,
what I'll
I'll
just
just
do, I'll
compare
just
the
compare the
distance.
distance.
Let's say this
Let's say
distance
this
with the
distance with
origin,
the origin here,
and this
and
distance
this
turns
distance
out to be
turns out
more
to be
than
more
this.
than this, right?
Sorry, smaller
Sorry,
than this.
smaller than this.
So we can see
So we
this
can
is
see
your
this is your distance, right?
f of x
F of
mod,
x mod,
and this is your
and
m
this is your
distance.
m distance.
So we can
So we
see
can see f of x
mod is,
mod is,
oh sorry, I have
oh sorry,
used
I
a
have used
wrong.
a wrong.
I'm sorry.
I'm sorry.
This is true.
This is true. Sorry.
Hmm.
Hmm.
So what I
So
see
what do I
here
see here
is that mod
is
of
that
f
mod
of
of
x
f
is
of x
less
is
than
less than
m.
m.
No matter
No
what
matter
point you
what
select,
point you
for
select,
example
for
this,
example this,
over here
over
also you
here
can
also
see
you
this
can
is
see this
mod
is
of f
mod
of
of
x,
f of x,
and
and
the
the
correspondingly you have the
correspondingly you have the
distance m.
distance m.
You can
You
compare
can
this
compare
distance,
the
vertical
distance, right?
distances.
Vertical distances.
So
So,
so this is what
so
this
this is what
above
this above
definition is
definition
trying to
is
tell
trying
you.
to tell
We're
you.
just trying
We're
to
just trying to
compare
compare
two
two
distances, and we
distances,
found
and we
that
found that
no matter
no matter
what the value
what's
of
the
f,
value of fx,
it's
it's
always
always
within
within
some
some
particular m.
particular m.
Okay,
Okay.
so that's what
So
the
that's what the
definition of
definition of something called as a bounded.
Yes.
Is
I hope this
I
all
hope
idea
this
is
all
clear
idea is
to all.
clear, right? To all.
If function is
If function is
bounded,
bounded,
then we say
then we
that
say that the range of function is also bounded
because
because
the range
the
is
range is
basically
basically
the
the
possible
possible
values of the
values of the
function
function,
outcomes,
outcomes,
the
the
possible
possible
outcomes.
outcomes.
And if the
And
function
if the
is
function is
bounded,
bounded,
because what do
because
we mean by
what do we mean by
boundedness?
boundedness? Boundedness means that all possible values of f
Can be
can be
contained
contained within a container.
we can make a
We can make a
container
container
around it.
around it.
So this is a
So this
double
is a
implied
double
statement.
implied statement, right?
So
So if someone tells you that the range of the function is bounded,
we can
we can
immediately
immediately
conclude
conclude
the function
the
is also
function is
bounded.
also bounded.
And it turns
And
out
if
the
turns
function
out
is
the function
bounded,
is
that means
bounded,
it
that
can
means
be
it can be contained
within
within some limits, some
some horizontal lines.
horizontal lines. Then we
Then we
can
can
say
say
that the
that
function
range is also
range is
bounded.
also bounded.
This is an
This is an
important
important
statement.
statement.
Okay.
Okay,
And
and
and we say
and
that
we
the
say that the
function is
function
set to
is set
attain
to attain
its
its
bounds
bounds
if there
if there
exists
exists C and D, and
C&D
C and D
basically the
basically
point
what
of
the point of
maximum and
maximum
point
and
of
point of
minima.
minima, right?
Global maximum,
Global
global
maxima,
minima.
global minima.
I mean
I
those
mean
values
those
of x
values
for
of
which
x for
we have
which we have,
at
at
best
best possible outcomes,
best in the
best
sense
in
of
the sense of
maximum and
maximum and
minimum.
minimum, right?
So
So
this is what
this is
we
what we
say that
say that
a function
a
is said
function is
to
said to
attain its
attain its
bound,
bound,
attain its
attain
bound
its bound
when we have
when
this
we have this
situation,
situation,
when there
like when
exist
there exist
certain
certain
inputs
inputs for which
the
the for which if we calculate the value that turns out to be the maximum of the function and
minimum of the
minimum
function
of the function
correspondingly.
correspondingly.
So that's the
So
whole
that's the
idea.
whole idea of it.
Now we will move
Now we
out
will
to the
move out
next
to the
point.
next
We
point.
have this
We have
particular
this particular
example.
example.
In this
In this
example, we can
example, we
see
can
that
see we have a function over here.
is defined
This is
from 0
defined
to
from
1
0 to 1,
and x
and
equal to
x
0
equal
it
to
is
0
defined
it is
as 1.
defined as 1.
And we just
And
want
we
to
just want to
illustrate the
illustrate
idea
the idea over here that
the function
this
is
function is
bounded below,
bounded below,
but this
but
function
this
is not
function is
bounded
not
above.
bounded above,
And hence
and
this
hence
overall
this
function
overall
is not
function is
bounded
not
at all.
bounded at all,
Because
right?
you can
Because
bound
you
from
can bound
below,
from below, but you cannot bound from above, right?
and above it
And
goes
above
to
it
some
goes to some infinite value,
very
a
large
very
value.
large value.
So
So,
losing the
so losing the
continuity is very
continuity is
important
very
issue.
important issue.
So let's say you
So
have a
let's say you have a
situation. In this
situation.
case,
In
we
this
can see
case, we can
here
see here
we have
we have
lost the
lost
idea of
the idea of
continuity.
continuity here.
So the moment
So
you
the
lost the
moment you
idea of
lost the idea of
continuity,
continuity,
you have
you
also
have
lost
also
the
lost the
you have to be
you
very
have to be
careful
very
when we
careful
talk
when
about
we
the
talk
being
about the
bounded
being bounded,
because you might
because
have
you
a
might have a
continuity which is
continuity which is like an infinity type of continuity.
then over there you
Then
can
over there you
just
can just immediately write down the function is not
bounded at all.
bounded at all.
In this case you
In
can
this
see
case, you
very
can see very
carefully
carefully here.
and
And
here I have
here I have
repeated
just
the same
repeated the same
example
example
here.
here.
Uh,
Uh,
now my next
Now
goal
my
is to
next goal is to
basically
basically
make
make
you
you
understand
understand
what
what
do
do
you
you
mean
mean
by
by compact and
not compact.
not compact.
Okay,
Okay.
so what we see
So what
that
we see that
the definition
the
of the
definition of
compact
the
is
compact is,
so this is your
so this is
definition
your
of
definition
something
of
called as a
something called as a
compact.
compact.
Compact
So
basically
compact
tells
basically
you when
tells
an
you when an
object is said
object
to
is
be
said to be
closed
closed
and bounded.
and bounded.
So we
So
understood
we
what is
understood what
mean
is
by
mean
bounded.
by bounded.
The idea and the
The idea
notion
and
of
the
the
notion of the
boundedness is
boundedness
clear
is
to all.
clear to all.
But we still
But
don't
we
know what
still
do we
don't know
mean
what
by
do you mean by something called as a closed.
right.
Right?
So the moment
So
we
the
found
moment
that
we
we
found
have a
that we have a
set
set
which is
which
bounded
is bounded
and
and closed,
then I can
then you can
immediately
immediately
conclude
conclude the
the
particular
particular
set
set is
is
compact.
compact as well.
And this is
And this
true
is
vice
true
versa.
vice versa.
We can use
You
this
can use this
statement in
statement
both
in
sense,
both sense,
right?
right?
And if you find a
And if you
particular
find a
object
particular
which is
object
said to
which
be
is said to be a
compact,
compact,
we can say
then
this
you can say
particular
this
set is
particular set is
closed
closed
and
and
bounded
bounded
both.
both.
And let's move
And
on to
let's
the
move
idea.
on to the idea.
Like for
Like for
example,
example,
so before
so before
understanding
understand
what do we mean
what
by
do you mean
closed,
by closed,
we'll first try
we'll
to
first try
understand
to
what do you
understand
mean by
what do you mean
open
by
set,
open set.
what do you mean
What
by
do you mean by
interior point.
interior point?
Because
Because
the
the
moment
moment
you
you understand
understand
what
this,
is interior point,
we can
we
immediately
can
understand
immediately
what do you
understand
mean by
what you mean
open
by
set.
open set.
And the moment you
And the moment
understood
you
the open
understood the
set,
open set,
the idea
the
of closed
idea
set is
of closed set is
straightforward.
straightforward.
So this is the
So this is the
hierarchy to
hierarchy to
understand
understand
the
the
notions,
notions,
various
various
ideas in
ideas in the
mathematics.
mathematics.
For example,
For
here I have
example,
taken
here
an
I have taken an
example of
example of a
here I've
here
wrote
I've
down the
wrote down the
definition of
definition of
interior point.
interior point.
And in this
And
case,
in
we
this
can see
we
that
can see that
a
a
point
point
is said
is
to be
said to
an
be an
interior point.
interior point.
Let's say there's a
Let's say
point
there is a point
which belongs to
which
set
belongs to
S.
set
Here I have
S. Here I
shown
have
this in a
shown as in a
diagram.
diagram.
You can see
You can
that
see from here in this diagram,
let's say.
let's say.
So you can see
So you
this
can see
red
this red
encircle,
encircle, this, this
this closed figure. You can see this black. and let's say I have a point in a set S, and I just want to understand whether this point is a close, this point is interior point or not. I just want to understand. And in this diagram, I have illustrated 2 points, one said to be interior point and another is not an interior point. Okay, these are boundary points. We can say the
We
point
can
which
say
I
the
have
point
marked
which
at
I
the
have marked at
boundary,
the boundary,
which lies
which
at the
lies at the
black circle.
black circle, which is
You
a,
can see here,
you can see here,
this particular
this
point,
particular point,
this one
this one
is a boundary
is a
point.
boundary
This is
point.
not an
This is
interior
not an
point,
interior point
because no
because
matter
no matter
what
what
circle you
circle you
construct around
construct
this,
around this, no matter what kind of
a
a
neighborhood
neighborhood
you try
you
to
know you try
construct
to
around this
construct around
particular
this
boundary
particular
point,
boundary point,
no matter
no
how big
matter
or
how
small
big
this
or small
neighborhood
this
is,
neighborhood is,
this
this
neighborhood
neighborhood can never be
can never
completely
be inside
inside
this
this
set
set
S.
S, right?
This neighborhood
This
can never
neighborhood
be
can never
inside
be inside
the set
the
S.
set S.
Okay, no matter
Okay,
how
no
large
matter
and
how
small you
large and
select.
small you select.
But you can see
But you
this
can see this
particular point,
particular
and
point,
I say
and
that
I
this
say that
point
this
is
particular
an
point is an
interior point
interior point
because
because
there exists
there
a
exists
small
a
neighborhood.
small neighborhood.
You can always
You can always
construct
construct. You are always able to construct an
around
interval
it,
around it,
small
a small
neighborhood
neighborhood around it,
which lies
which lies
completely inside
completely inside
this set
this
S,
set S,
right?
right?
So that's what
So
the
that's what the
definition of
definition of
interior point
interior
is.
point is. Here I've shown it as a diagram.
Now we will see
Now we
that
will see that in
in
a
epsilon delta
epsilon delta definition, which is the interval definition. So we say that the point as x is said to be an interior point
when there
when there
exists
exists
a
a
neighborhood,
neighborhood,
when there
when there
exists
exists
a
a
particular
particular
neighborhood
neighborhood or
or some
some
particular
particular
vicinity.
vicinity.
Maybe you can
Maybe you
create
can
a
create
set
a
around
set
it,
around
small
it, small
subset.
subset.
You can see this
You
is
can
a
see
small
this is a
subset.
small subset, right?
So this
So
subset
this
lies
subset lies
completely
completely
inside the
inside the
original set.
original set.
If
So
that's
if
true,
that is true,
then we say
then
that
we
this
say
is an
that this is
interior
an
point.
interior point.
This is a
This
boundary
is a
point
boundary point
because at the
because at the
boundary, no
boundary,
matter
no matter
how
how
small or big
small or
interval
big
you
interval
select,
you select,
no matter
no
how
matter
big or
how
small
big or small
neighborhood you choose,
neighborhood you choose,
you can never
you can
have
never
this
have this
particular whole
particular whole
neighborhood
neighborhood
inside
inside
the
the
set
set
S.
S.
So what do you
So
mean
what
by
do you
over
mean
here?
by
This
over
means
here? This means
contains.
contains.
Okay, this
Okay, this
notation
notation
means
means
contains.
contains. Okay,
So
so
that's the idea
that's the
here.
idea here.
I hope
I
everyone is
hope everyone is
able
following,
to follow
able
up.
to follow
Just
up,
give me
right?
one
Just give
thumbs
me
up
one thumbs up
if everyone
if
can
everyone can
understand.
understand.
I just need one
I just
thumbs
need
up
one thumbs up so that I can move forward, right?
because after this
Because
the
after
idea
this,
of
the
open
idea
set
of
is
open
very
set is very
straightforward.
straightforward.
It's
It's
in
in
your
your
screen.
screen itself, right?
I can
I can
I can
I can
basically
basically
illustrate the same
illustrate the
point with a
same point with
live
a
example
live
here.
example here.
In this I have
In
a
this, I
set.
have a set.
The set
The
is
set
starts
is
from
starts
zero
from
and
zero
ends with
and
one.
ends with one.
Okay,
Okay,
and
and
what do we see
what do we
here? That
see here? That
I have a
I
point
have a point,
and I call
and
that
I call
set to
that
be
set to
an
be
interior
an
point.
interior point,
And this
and
interior
this
point
interior point
is called
is called
interior point
interior
because
point because
I can always
I can always
construct
construct
a small
a small
subset around
subset
this
around this
interior point,
interior point,
and this
and
set
this set
contains inside
contains
the bigger
inside the bigger
interval.
interval.
So this is the
So this is the
definition of
definition
interior
of
point,
interior point,
and this is how
and
we
this is how we
illustrate
illustrate
using this
using this
diagram,
diagram,
using
using
this
this
epsilon delta
epsilon delta
definition, and
definition,
here is an
and here is an
example.
example.
Okay,
Okay,
so an open
so
set
an
is
open set is said to be an open
a set is
a
said to
set
be
is
an
said to
open
be an
set
open set
if all
if
its
all
point,
its point,
I
if
consider
I
all of
consider
its
all of
point
its point of
of
this
this
particular
particular set
set
are
are
interior points.
interior points.
So you might
So
have a
you might have
situation
a
in which
situation in which
you have this
you have
boundary
this
points
boundary points,
and you hope
and you hope
you don't have
you
these
don't have
boundary
this
points in
boundary
your
points
given
in your
set.
given set.
If you have
If you
these boundary
have
points
this
in your
boundary
given
points
set,
in your given set,
then you might
then
not
you
have
might
this
not
open
have
set
this open set, right?
because the
Because
moment you
the
have this
moment you have
boundary
this
points,
boundary
because
points,
no matter
because no
how
matter
big or
how
small
big or small
neighborhood you
neighborhood
choose,
you choose,
you cannot
you cannot
have this
have this
particular subset
particular subset
completely
completely
inside
inside
this
this
given
given
set,
original set,
right?
right?
So I better
So I
don't
better
have this
don't have this
particular
particular
boundary.
boundary.
The
So
kind of
the
image
kind
you
of
can
image you
have
can
in your
have in
head
your
is
head is
basically
basically
this
this
set
set
S
S,
where you have
where
this
you have
fuzzy
this
boundary,
fuzzy boundary,
where you don't
where
have
you
this
don't
particular
conclude this
boundary at all.
boundary at all.
You have this
You have this
each and every
each and
point
every
but not the
point, but not
boundary.
the boundary.
Okay, so
Okay,
that kind of
so that kind
image
of
you
an
can have
image you
for
can
this
have for
open
this
set.
open set.
But now the
But
moment
now
you
the moment you
understand what is an
understand what
open
is an
set,
open set, So the closed set idea is very simple. Just take the complement of the open set. You will get your closed set. Because open set plus closed set forms completeness. Okay. So anything which is not inside this open set, definitely that will contain inside this closed set. So you can say a set to be closed if its complement is open, right? So the moment so how you can you create an closed set? Just take an open set, take complement of that open set. Now the result is that you have a closed set. So the idea of closed set, open set, interior point, and something called as a bounded, which I have discussed here. Hopefully, all these ideas are clear to you all. We can discuss this further if you have any doubts. Okay. Now we'll move on to the next set of definition. There is something called as closed interval because closed interval is one of my favorite ways to think. Um, okay. So what do we see that this closed interval? I call this closed interval to be a compact set, and this can be one of your MCQ question. They will give you a set and they will ask you just write down how many compact sets are available here. And the moment you see any closed interval, the first thing which should come into your mind that is a compact set. And why am I saying that it's a compact set? Because the first thing, in order to be a compact set, that need to be bounded. And the second point, it should satisfy that it should be a closed set, right? Yeah. So you can see this. Uh, Over here, I have this real line, right? In this real line, I have basically marked out my closed interval. In this real line, I marked out my closed interval, and I'm calling that this particular set, including the boundary point, which I've showed in the red color, is a closed set. And why am I calling that as a closed set? If I take a complement of it, and if I say what's the complement set over here, if someone wants to know the complement set is basically minus infinity to a open. See this very clear. This is an open union b to infinity. So this is an open set, and you can see this is an open set, and this is an open just because from the left hand side you cannot bound, from the right hand side you cannot bound it. You can see from the left you cannot bound, from the right you cannot bound, and also this is not bounded within as well, right? So we can see this that particular thing which I've marked here is closed as well as bounded. So together it's a compact set. So what we can conclude that all closed intervals are compact sets. So the next immediate question comes out to be, is R a real number is a closed? The answer is yes. Why is it closed? Because if you take a complement of a real number, which is a null set, right? And null set is open. Null set is open, right? So that's the logic behind this. Why this real number is a closed set. Even though this sounds to be little uncomfortable, but real number is a closed set. Is the real number is a bounded set? No, real number is not bounded. Real number is not bounded because it cannot fit the boundedness definition, right? Because the idea that there exists this large k value, the idea that there exists a large k value, the existence of such, upper and lower bounds do not exist, right? Hence, real line, hence real line, hence real line is closed but not bounded. So overall, real line is not compact. So that's the idea. Now we would like to see the situation in which we have a set and it's compact, okay, and the function has this particular idea. So what do we see that? We see that there is a function which takes in which the domain is S, and here the domain S is basically compact object, right? It's a compact in the sense it is closed and bounded. So what do we see that? Then the range of the function is also compact. You might have a situation, right? For example, you want to see this in a more easy fashion. The way you can see that there is a function in which the input is this particular interval, right? You can have any values from starting from A to B, right? And A and B both are included. And the moment I say that whenever I feed and compact set as an input, you can say that the range of f is compact. So the range of function is bounded. So there always exist, you know, maxima, minima, such that the function can be bounded. Okay, so that's the idea here. The last point of the discussion before I close this session is to talk about what do we mean by supremum and infimum. So these are important definitions because you will be using this everywhere, and you can expect at least couple of questions from in supremum and infimum. At least you can expect. And the assumption behind this particular supremum infimum is that we just want to understand whether this set exists such quantities or not. And in this case, we are assuming the set is not an empty set. There exist some values because for empty set, these definitions don't make any sense. So in order to define what do you mean by supremum and infimum, which is a very important quantity because they are unique points, we want to understand what do we mean by the supremum and infimum word. And the assumption is that the set is not empty set. So some elements are there. So what do we see that supremum can be called as a least upper bound. You can say this is an alternative word for this supremum. For example, those who don't know what is mean by supremum, you can tell them that supremum is nothing just a least upper bound. Since you know that upper bound and lower bound is not unique. For example, I can illustrate that idea over here. Like for example, in this particular plot, you can see I can always come up with a point. I can always come up with a horizontal line. For example, this. Let's say a sum y equal to a. This green color horizontal line can also act as a lower bound for this function. I can come up with another interesting lower bound. For example, this. Let's say y equal to b. This orange line can also act as a lower bound for this particular function. So our idea is that the bound is not unique. Bound is not unique because all three of them act as a bound. All three of them can be seen as a bound to this function. But we want something which is unique and more useful because you are not interested in this, orange and this green, right? Even though they are bound, but you are not much interested. But there is a very important unique bound to which you can be very interesting, to which you might be very interested, and that is called that to be greatest upper bound, greatest lower bound, right? Which just touches the function from the lower side, just touches the function. For example, like for example over here, it just touches, right? Over here you can see. So you might be interested in this line because this might be important to you. Some greatest upper bound, GUB, which is what we call as in a simple language we call this as infimum, right? So we always want to calculate what are infimum and supremum because they are the actual useful quantities, right? Let's say you have a machinery in which you have to pay cost. The more and more you go in this direction, right? So I want to minimize my cost of doing the machinery thing. So I would like to calculate what is this infimum because this infimum will lead to my optimized value, right? Because just having this situation is less expensive compared to this situation. So I want to make my function to go as negative as possible. I don't want that to happen because I have a machinery problem. So I will always want to calculate what is my infimum, the greatest lower bound. Okay, so this is the idea behind this. So this is the philosophy behind this. And yeah, so here it is. So the idea is that you and these bounds are basically unique bounds, and this is shown in this particular illustration. For example, you have an interval 0,
1,
1,
and I call
and I
that
call
0
that
to be
0 to be
greatest lower
greatest
bound
lower bound and 1 to
and
be
least upper bound,
least upper bound,
right?
right?
And you can see
And you can
here
see
the
here
salmon,
the salmon
red color,
red
salmon
color,
pink, I
salmon
guess,
pink, I guess,
over here.
over here.
All these
All
points
these
in
points in this
red
particular
color
color
are all
are
my
all my
lower bounds.
lower bounds.
All of my
All
them
of
are
my
lower
them are
bounds.
all lower bounds.
But this
But this
0
0
is also a
is
lower
also
bound.
a lower bound.
But 0
But
has some
0 has some important
special
special
property
property
compared
compared
to
to this
all other lower
all other
bounds,
lower bounds,
that it is
that it is
greatest among
greatest
all the
among
lower
all the
bounds.
lower bounds.
So that's why I
So
call
that's why
this
I call
0
this 0 as
to
to
be
be
my
my
greatest
greatest
lower
lower
bound.
bound.
And over
And
here,
over here, which I see, you can see over
on the
here
right
on the
side,
right hand side,
is that you have
is
this
that you have this
greatest
greatest
upper bound,
upper bound,
because all the
because
points
all
in
the
this
points in
red
this red
are my upper
are my
bound.
upper bound.
But
But
this one
this one
is my
is my
lowest
lowest
among
among
all the
all
upper
the
bounds.
upper bounds.
And I'm
And I'm
interested in this
interested in this particular
lower
lower
bound and this
bound and this upper bound,
because
because
I might be
I might be
interested
interested in
in
just
this,
within this,
within this
within this particular
values,
values,
because
because
exploring this value
exploring this
might be
value might
costly
be
for you,
costly for you,
right? So we
right?
just
So
want
we
to
just want to
know what are
know
these
what are these particular
unique
important
bounds,
unique bounds,
because when we
because
say
when
the
we say
function
the
is
function
bounded,
is bounded,
for example
for
when you
example,
become
when
an
you become an
engineer,
engineer,
so whenever
so
your
whenever
boss
your
asks
boss
for the
asks for the boundedness of your work,
like
like
what is the
what is
bound
your
on
bound
your
on your work, what
bound,
is the bound, whenever
whenever the
the
discussion of bound
discussion of
comes,
bound comes,
so they
so they
always
always
mean to this
mean to
values,
this values.
the greatest
Yeah, the
lower
greatest
bound
lower
and
bound and
lowest upper
lowest
bound.
upper bound.
So whenever
So
someone
whenever
loosely
someone
asks you
loosely asks you
what is the
what
bound
is the
on
bound
this,
on this,
what is the
what
bound
is the
on that,
bound on that,
we mean
they mean
this,
this,
okay, not the
okay,
other
not the
values.
other values.
And over
And
here
over here, I have just wrote
in the sense
in
of
the sense
epsilon
of
delta
epsilon delta
definition,
definition,
where we can
where we
say
can
that
say that
here I just
here I
explained
just
what do you
explained
mean
what
by
do
an
you
upper
mean by an
bound
upper bound
and lower
and
bound.
lower bound.
You can just
You
check
can
out
just
them.
check out them.
They're very
They are
simple.
very simple.
So whenever
So
we have
whenever we have
a value
a value
which belongs
which
to a real
belongs to a
number
real number,
such
such
that
that
this value
this value
is greater
is
than
greater
all
than all
possible values
possible
inside the
values
given
inside the
set.
given set.
Let's say if we
Let's
just
say
want
if
to
you just want to
calculate
calculate
what
what
is
is
the upper
the
bound for
upper
this
bound
set,
for this set,
and I claim
and
that
I
this is
claim
my
that this
upper
is
bound,
my upper bound,
if and
if
only
and only
if that
if
particular
that
alpha
particular
which
alpha
I
which I
claiming that to be
claiming
an
that
upper
to be
bound
an upper
is
bound
greater
is
than
greater
all
than all
values
values of
in the set.
in this set, right?
So this is how
So
I
this is
define
how I
my upper
define my
bound
upper bound and
and
lower
lowest
bound. You
bound
can
very
just check them
easily.
very easily.
And there are some
And there is some
axioms.
axioms.
So this
So
axiom
this
basically
axiom
tells you
basically
that
tells you that
there always
there
exists
always
such
exists
point.
such point.
The existence
The
of
existence
greatest
of
upper
greatest
bound
upper
and
bound
lower
and
upper
lower
bound
upper bound
is always
is
exist.
always exist.
They always
They
exist.
always exist. Okay.
Uh,
Uh,
they always
they
exist
always exist
with the
with the
condition that
condition
the
that
set
the
is not
set is not
empty set.
empty set.
With the
With
condition
the
that the
condition
set
that the set
is not
is
empty.
not empty.
Uh,
Uh,
over here,
Over
I
here, I
have
have
used
used
the
the
definition
definition
of
of
least upper bound
least
and
upper
greatest
bound
upper
and
bound.
greatest upper bound.
And here I'm
And
trying
here
to
I'm
make you
trying to make you
understand
understand
using this
using
same
this same
comparison method
comparison method
what we have
that
did
what we
here.
have did here,
The same
the same
comparison method, and
comparison
I
method,
claim
and I
that
claim that
my x is
my
the
x is
lowest
an
upper
lowest
bound
upper bound
of this
of
particular
this
set
particular set
S.
S.
So if
So
there
if
exists
there
an upper
exists
bound
an upper bound
which is greater
which
than
is
that
greater than
particular
that
claim,
particular claim,
right?
right?
Then basically
So
what I'm
basically
doing
what
here,
I'm doing here, I'm
I'm
basically
comparing all
comparing
my
all
upper
my
bounds,
upper bounds,
and I say
and
that
I
the
say
one
that the
which
one
has the
which
very
the
lowest
very
value,
lowest value,
and I say
and I
that
say that
to be in my
to be in my
least upper bound.
least upper bound.
So this is what
So
I
this
have
is
done
what I
here,
have done here,
because I can
because
always
I
come
can
up
always come up
with a
with
upper
a
bound
upper
which is
bound
less
which
than
is
all
less than all
possible
possible
upper bounds,
upper bounds, right?
because I can
Because I
create a
can
set
create a set
using this.
using this,
How
right?
can I
How
create the
can I
set?
create the set?
I'll
I'll
just
just
pick
pick
all the
all the
values
values
which
which
satisfy
satisfy
this
this
and
definition.
make a
I can
set.
make a set.
And from this
And
set,
from this set,
I'll just
I'll
compare
just
among
compare
them
among themselves and just
and see
see
which
which
one
one
is
is
the
the
smallest.
smallest. So that's the idea.
I just want
I
to,
just want to,
you know,
you know,
tell you the
just tell
most
you
important
the most important
part of this
heart of this
supremum
supremum
infimum
infimum
idea
idea
is that
is that let's say you have
you have a
this
good old
good
situation
old situation
in which you
in
have this
which you have this
0
zero
as
and
an
one
open
as an
interval
open interval,
and 0
and
is
zero
your
is your
greatest lower
greatest
bound
lower bound and one is your
least upper bound,
least upper bound,
which we also
which
call
we
them
also
as
call them to be as infimum and supremum respectively.
so what do we
So what do we see that
all these
all
blue
these
values,
blue values which you can see, which all these blue points over here,
they can
they
never be a
can
lower
never be
bound,
a lower bound,
right?
right?
You need to be very
You need to be
understand
very
that
understand. They can never be a lower
that's the
bound. So that is the
significance of finding
significance
out
of
the
finding out
infimum,
the infimum.
because the
Because
moment
the
you know
moment you know what is an infimum,
you can
you
because
can, because
infimum
infimum
just
point just
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 divide the whole
divides
line,
the whole line. They divides the line into
one
one
in which we
in
call
which
as
we
an
call as an bound,
in which
in which
cannot have
you
a bound.
cannot have a bound.
So that's why
So that's why they are very important. And similarly over here in the
opposite side as
opposite
well,
side as well,
this
this
yellow dots
yellow dots
can never be
can
an upper
never be
bound.
an upper bound.
So this is the
So
role
this
of
is
the
the role of the
supremum and the
supremum and the
infimum.
infimum. It just
Break the line
breaks the
into
line
two
into
set,
two set,
in which
in
the other
which
set
the
is
other
the
set is the
bound set,
bound set.
can be
It
upper
can
and
be
lower.
upper and lower,
Another
and
set
another set
do
do
not
not
participate
participate
in
in
any
any
kind
kind
of
of
upper
upper
bound
bound or
thing
lower bound thing
business.
business. Okay.
And here is a
And here is a
simple
simple
proof
proof
which is done
which
in
is
a
done in a
classroom. You can
classroom.
see.
You can see. Maybe I
Maybe I
can
can
discuss
discuss
this
this
in
in
a
a
next
next
session
session
in
in
detail
detail
the
the moment
moment
I
I
get
get
the
the
response
response
for this.
for this.
So
So
that's the idea.
that's the idea.
And here I have
And here I
taken
have
some
taken some
example like
example like
what happens in
what
the case
happens in
of
the case of an open interval, what happens in the case of
closed interval.
closed interval.
In the case
In
of
the
open
case of
interval,
open interval,
and also in the
and
case
also in
of
the case
closed
of
interval,
closed interval,
your boundary
your
points
boundary points
are always
are always
act as an
act as an
infimum and
infimum and
supremum.
supremum.
And
And
you
it
just
just
compare.
compare.
So it doesn't
So
matter
it
whether
doesn't
your
matter whether
interval
your
is
interval is
closed or
closed or
your boundary is
you're
open.
open.
But still,
But still,
this is true.
this is true.
What you have
What you have
discussed in the above
discussed in the
cases.
above cases.
The caution
The
comes when
caution
you
comes
have
when you have
a
a
discrete set.
discrete
For
set, right?
example,
For example, you have a
you have
discrete kind of a set.
this
You
kind
have
of
this kind of
union kind of
union kind
business
of business where you
where
have
you have
this
two parts.
two part.
Let's say you can
Let's say you can,
let's say you have a
let's say
two
you have a
part
two part
of the set
of the
S
set
which is
S
continuous
continuous and it is
attached
attached
with another
with
discrete
another
point.
discrete point.
So in these
So in
cases
these
you need to be
cases, you
very
need to be
cautious
very
because
cautious because in these cases,
you cannot
you
have
cannot
this
have this
to work with,
to work with,
because in this
because
case
in
you have a
this you have a
continuous set.
continuous set.
Here we don't have
Here
a
we don't have a
continuous set.
continuous set.
You can
You
see
can
here we
see
have a
here we have
discrete
a
point, then
discrete
we have
point,
a
then we have a
continuous
continuous set. You
set.
have discrete point.
In this case you
In
can
this
see
case, you can see you have a continuous point. Here we have discrete point.
so you have to be
So you
very
have to be very
cautious
cautious
this
with
particular
this particular
situation
situation
where this
where
analysis
this
don't
analysis
work.
don't work.
Okay.
Okay.
I will
I
discuss
will
this
discuss
in next
this in
session
next session,
where I will try
where
to
I will
give
try to
you
give
the
you the
definition of a
definition of a
limits
limits
in the
in the
perspective of a
perspective of a
sequence.
sequence.
Now I will not
Now I
cover
will
them.
not cover them.
Um,
Um,
Hopefully everybody
Hopefully everybody
understood
understood like
till
so
now.
far till now.
I will cover
I will
this
cover
one
this
page.
one page only.
I will start
I will
from here.
start from here, then I'll
Then
go
I'll
to
go to
the
the
newer
definitions and
definitions and
ideas.
ideas.
But I will start
But
from
I'll
here.
start from here.
Over here I will
Over
try
here,
to
I
give
will
you
try to give you
you know the
the
definition of a
definition of a
limits
limits
in the terms
in
of
the terms
sequence
of
language,
sequence language,
because there are so
because there
many
are
ways
so
you
many
can
ways you can
approach
approach
to a given
to a
point.
given point, right?
So the
So
earlier
the earlier
definition what we
definition
have
what we
seen,
have seen,
like for
like
example
for
here,
example here
in this
in
case,
this case,
we
we
approach
approach
this limiting
this
point
limiting point
continuously.
continuously, right?
But the problem
But the
is
problem is
that
that
in your
in
real
your
life
real
problem,
life problem,
you cannot
you
go
cannot go
continuously
continuously, right?
because that's an
Because that's an
expensive
expensive
process.
process.
So what you do,
So
you
what
go
do you
in
do? You go
discrete
in
steps
discrete steps
and check
and check
whether they
whether
exist or
they
not.
exist limit or
Because in
not.
order to
Because in
check
order to check
in this
in
way,
this way,
you need to go
you need to go
continuously.
continuously.
But
But
going,
going, but the approaching
in
something
a
which in a
continuous fashion
continuous fashion
is not
is
easy.
not easy job.
It's very
It's
very
very
difficult.
very difficult.
So what you can
So
do
what you
at
can
best
do at
is to
best
go
is to go in a
in a
discrete
discrete fashion
fashion
and check whether
and
this
check
limit
whether this
exists or
limit
not.
exists or not.
And the way you
And
can
the
go
way
in
you
a
can go
discrete
in a
fashion
discrete fashion
by using the
by using
concept
the
of
concept
limits.
of limits.
So
So by using the concept of sequence,
right,
right?
where
Where
you will
you will
approach
approach
this particular
this
limiting
particular
value.
limiting value.
Sorry,
Sorry,
where you
where
approach
you approach
this limiting
this
value,
limiting value, which the point at which you were interested to calculate the limit in a discrete fashion. You can say the first sequence, second, third sequence.
you can go
You
very
can go very in
discrete
a discrete
steps,
steps,
right?
right?
And you try to
And you'll
approach
try
this
to approach
particular
this
point.
particular point.
So over here
So
you
over
will
here you
see
will
the
see the
definition in that
definition in that
sense.
sense.
Okay.
Okay.
So that's it
So
for today.
that's it for today.
Do you guys have
Do you
any
guys
question?
have any question?
If not, we can
If not,
stop
we
this
can
meeting
stop this meeting here.
and we can
Again,
start
start
in next
in
session,
next
next
session,
Monday.
next Monday.
Any thumbs up?
Any thumbs up?
Hopefully
Hopefully,
you all guys
you
got
all
the
guys
idea.
got the the idea. I'll upload this video on YouTube so that you can check them later.
Okay, see you guys.
Okay,
See you guys
see you
later.
guys later.
Bye.
Bye.